So I will chair the first session of this morning, and this is the last day of the micropropulsion and CubeSat workshop. So time flies. It was it went very fast. We had very great, good talks during the last 2 days, and I'm pretty sure it will be the same today. We will have very interesting papers. I want to remind you guys that at 4 p.m. today, there will be a second roundtable about technology. The previous one yesterday was more focused on science. This one is about technological development. I just remind you the title: Micropropulsion for Small Satellite, Trends and New Opportunities. So I really advise you to join. We will have very great speakers. We will have people from the CNES and ESA, and we will have people from Exotrade, Trust Me, ENI Space, Gamma, Impulsion, T4I, and COMAT. So we have a super panel list with very good speakers and experts. So I really advise you to join today at 4 p.m. So this morning, before the break, we'll have two invited lectures. The first one is from ENI Space company in Spain, and the second one will be given by CNES people. For the first one, there will be two talks, one given by Sarah Correiro, and the other one is given by Giuseppe Di Pasquale. What I propose, if you agree, is that you just talk during half an hour. So the two talks one after each other, and then we will take all the questions concerning the first and the second talk at the end during the last 10 minutes. Do you agree with that, Sarah and Giuseppe?
Yeah, I think it's perfect. Stefan.
Okay, we do that. So Sarah, I will give you the floor. So you've got more or less 15 minutes, and Giuseppe will have, again, 15 minutes behind you for your papers. Okay, so I leave the floor to you, and we meet in half an hour.
Okay, perfect. Thank you, Stefan. So let me share my screen. Okay. Can you see my screen properly?
Yeah, it's perfect.
Okay, cool. So thank you very much. Good morning, everyone. Well, it's a pleasure for us to be here today presenting our latest technological developments at the ENI Space. As Stefan was saying, this talk will be split into main parts. First of all, I will talk about Athena, about our electric propulsion system. And just after me will be my colleague, Giuseppe, who will explain and present all our software developments more related to ENI Go and ENI 360. Okay, so I would like to start this talk sharing with you some numbers. Here you can see, for instance, the percentage of nanosatellites and CubeSats which have actually included some kind of onboard propulsion at the moment they were being launched. So I think this is quite impressive. No? We can see that in the nanosatellite class, this number is below the 6% historically, while, for instance, in the microsatellite and in the small and medium satellite class, it's above the 75%. So one of the things that we want to do at ENI Space, one of our main goals is actually to reduce this gap, and we pretend to do this by allowing to any kind of nanosatellite to actually include onboard propulsion. So before I go on, I think it's interesting if we have a look. I just checked a couple of days ago how is this number looking in 2021. And I have to say that this number is currently this year close to 12%. So this is amazing. No? If I remember correctly, I think 35 nanosatellites and CubeSats which were launched this year actually were launched with onboard propulsion. So I think these are great news for the community, and we are definitely in the good way to go. Okay, so why do we think this problem exists? No? At the ENI Space, our vision is that this is mainly due to three main things. First of all, there's a big platform variability. No? This means that, for instance, that it is nothing to do a 1-unit CubeSat with a 3-unit CubeSat with a 12-unit CubeSat. And not only this, but even in a 3-unit CubeSat, the power you have available on board depends so much on the number of panels, deployable panels that you actually have. No? So this means that the one-size-fits-all solution is that actually doesn't exist. Then secondly, there are the obvious restrictions in these very small platforms. When we talk about power, mass, and volume, which is something pretty obvious. But finally, but not less important, we have detected that there is a lack of dedicated knowledge when we are talking about propulsion and orbital dynamics in particularly in very small companies. So I think as the community of micropropulsion, we still need to do a little bit of effort there. So how do we pretend to tackle these problems? This is what we are doing at TNI Space. We are proposing a concurrent engineering design between the propulsion system and our software developments. My colleague Giuseppe will explain later more about the second part related to the software. And our electric propulsion system is Athena. This is what I'm going to talk today. It's about how is the status of the technology at the moment. Okay, so Athena stands for Adaptable Thruster Based on Electrospray for Nanosatellites. And it's a fully scalable solution based on versatile modular approach. Here you can see three pictures with, there are three renders with our Athena, how will Athena propulsion system will look, for instance, in a 3 unit, potentially in a 6 unit, and in a 12 unit, here, I think it's the two main characteristics of Athena, as I was saying, is that a completely customizable, versatile, modular propulsion system. And then the second, but not less important, is that we say that it's a thruster which is software defined. And this means that the thruster will be designed, taking into account both the requirements, not only from the platform, but also from the maneuver scenarios, from the mission analysis from the beginning. So it will be designed specifically for a specific mission. Okay, so the principle of Athena is quite simple. It's very known in the industry as the electrospray. It's an electrospray thruster. Here you can see a schematic of how it operates. So basically, we have these emitters. You can see some pictures there of real emitters. So we apply a high voltage between an extractor grid and the emitter substrate. And the liquid, which is the propellant, which is an ionic liquid, is just below, is stored in a porous reservoir, in a 3D printed porous reservoir. And once we apply the high voltage, since there's a concentration of the electric field on the tip of the cone, the liquid will feed the emitters and will be extracted and accelerated. So why do we think that electrosprays are actually one of the cleanest solutions and one of the best solutions for CubeSats and nanosatellites? Well, there are several reasons. First of all, we use ionic liquids as propellants. This means that we don't need pressurized deposits, that they are very, very stable in vacuum, and we can actually reduce up to 50% the dry mass of the system. Also, we are in purely electrostatic acceleration, so we don't have any magnetic elements, which means we also more reduction in mass. We can have net zero current without cathodes, which we all know that cathodes are the main life limiting factor in Hall thrusters, for instance. And we also can retain very high efficiencies at very low power. Okay, so here you can see how our engineering model looking at the moment. This is one of our latest pictures. Here, Athena is composed, as all electric propulsion systems, of three main parts. Okay, we have what we call the thruster stack, which in this case, it's composed of the meter and the grid. We have also applied for a patent regarding the meters. Then we have what we call the power processing unit, which is composed of a DC-DC converter, a switching board, and a controller. And then we have the propellant management unit, which in this case, it's as I was saying, it's a porous reservoir which stores basically the ionic liquid. Okay, so what I'm presenting today is what we are doing in the last months with what we've been doing at TNI Space is to actually characterize the performance of Athena, since this is absolutely clue and key in order to further develop the technology. So in order to characterize the performance, we are taking into account three parameters, let's say. We have obviously thrust, specific impulse, but also efficiency. And efficiency for us, like we always say, like it's the most important parameter that curiously nobody talks about efficiency. But efficiency means that if you have for the same ISP, if you have double the efficiency, you can have double thrust, or with the half of the power. So it's actually very important to retain high efficiencies, and particularly for small satellites and for microsats. So the total efficiency of the system, we need to take into account too, okay, what we call the thruster efficiency and obviously the efficiency from the PPU. The efficiency from the PPU, in our current prototype is 52%, but we expect to increase this efficiency to 80% with our new designs, and probably in the following weeks. Then regarding our thruster efficiency, in electrospace, this needs to be split in 4 different efficiencies. First of all, the energy efficiency, which takes into account the energy that actually sees the beam, the ion beam, the potential that actually is seen by the ions. We have the transparency efficiency, which basically takes into account the current that is actually extracted from the thruster. The divergence efficiency obviously takes into account the direction of the plume, and the polydispersity efficiency, which is related to the fact that we are extracting probably particles with different masses and with different velocities. Okay, so this is the prototype of Athena that we've been using in this test campaign. Here you can see at the top one of pictures with the microscope of our emitters. So it's 100 emitters in a 10 times 10 square millimeters. You can see here also an exploded view with the extractors, spacer, emitters, and this this porous propellant reservoir. So again, this is a passively fed thruster. So the propellant is being, let's say, the emitter is being fed by the propellant from below. And we are using for this test campaign, particularly the ionic liquid EMI BF4. Okay, so then these results that I'm going to show now have been carried in 2 facilities. One of them is the facility that we have at TNI Space, which is a 6-way vacuum facility. You can see at the left. And at the right, you can see the head-room vacuum facility at UC3M, at the Electric Propulsion and Plasma Group laboratory. Also, some of the results have been taken in this facility. Okay, so regarding the diagnostics, here there have been 2 main setups. The first of all is the one you can see at the left. We are using indirect performance characterization. All these diagnostics are being developed in-house by one of our colleagues. So here, basically, this setup, you can see we have three diagnostics: a Faraday cup that is going to do an angular scan of the current, the time of flight, which is the mass spectroscopy diagnostic, and the retarding potential analyzer, the RPA. So basically, in this setup, the diagnostics are fixed, and it's the thruster, which is going to rotate 270 degrees, is going to do the angular scan, then time of flight, and RPA. Here at the right, you can see the second setup, which was directly, we modified a commercial thrust balance, a Mettler Toledo, so it could be used in vacuum, and we're using directly this commercial balance to measure thrust. Okay, so let's go with the results. Here you can see for instance, our current voltage characterization at the left. This is very, very important because when the growth of this curve is exponential, it means that we are actually in the ionic regime, which is what we want for this kind of technology. Also, the onset voltage is currently below 900 volts, but with the new design, we hope that we can go below 600 volts. Here at the right, you can see how the thruster operates in the steady state operation of the thruster. So you can see the top figure is basically the voltage, which is going positive and negative. And here we have the emitted current of the thruster, which, as you can see, follows exactly the voltage curve. It's very important that we are doing zero, we are compensating in the duty cycle, so we have zero net current emitted from the thruster. Then regarding we use the RPA, as I was saying in this setup that the thruster is rotating, we use the RPA to measure the energy efficiency, which is currently at 99.2%. Then we have the Faraday cap. The Faraday cap is when the thruster rotates 180 degrees. We are collecting we see what is the collected current in the Faraday cap, so we can measure the divergence efficiency. So I think it's very interesting that you see that the positive and the negative beam are actually different. So this is something that we need to take into account, and we will further investigate. We have seen these results in the literature, by the way. And one thing that's important is that to take these measurements, what we were doing is like to stay 1 minute in each position at each angle, and then we do the mean value of the current, both in the positive and in the negative side for that angle. So it takes quite a long time to do the, the whole scan. Okay, then finally, this is the last result. I have to say that we are currently still calibrating the balance. So for instance, one thing that you can see in the picture is that when we were using this balance, that this test was just to analyze the thrust balance response mainly. You can see that actually the thruster has cables, so connected for this in this particular setup. So this was obviously could influence the measurement. So now the next results that we will hopefully present in the next couple of weeks will have the thruster will not have cables, but directly will be tested with the PPU. Here you can see the thrust, the pulse of the thrust balance. And this particular case was done here. You can also put the data like 0.32 watts of power. We have at 2.5 kV, 4,500 seconds of ISP and 10 micronewtons. So when we computed the efficiency of this of the thruster, taking into account this data, we have currently a 69% thruster efficiency, which matches pretty well with the results from the indirect diagnostics. Okay, so finally, and before I leave the word to my colleague Giuseppe, what can you expect from us on the following weeks and on the following months? We still need to develop the time of flight. Unfortunately, we haven't been able to present these results for this conference, but with the time of flight, we will be able to compute the polydispersity and we will have more accurate data. Also the transparency efficiency, and obviously we will perform a fully test campaign regarding the thrust measurements. And we are also moving from a 100-meter chips to a 385 meters. So our challenges are basically in the following months. It's to compute, perform lifetime tests, since we know that this technology, the life limiting factors are normally degradation and liquid bridges, and to qualify the system. So this is something that we are working on at the moment. Okay, so thank you very much. I will stop sharing now my screen, and I will leave the word to my colleague Giuseppe, and then you can ask all the questions that you need.
Thanks a lot, Sarah.
Thank you, Sarah. I'm going to share my screen. Just give me a second. Okay. Do you see my screen?
Yes.
Perfect. Okay. All right. So yeah. Okay. My name is Giuseppe Di Pasquale. I'm a mission analyst and industrial PhD at NA Space. And today I'm going to be presenting the other side of the NA Space, which is the software. So YANEGO N360, a software suite for micropropulsion system design and optimization. This work is carried out with some of my colleagues at NA Space and in collaboration with UC3M. So I'm going to jump right into the presentation. Well, okay, so as Sarah said, we see this issue, which is that one size doesn't fit all. And that's why for propulsion technology, we believe that it's important to have a modular approach, which is Athena, as Sarah described it. But this brings an issue, a problem, that's what we call the indirect problem. So in principle, now you have a propulsion system that has more, let's say, degrees of freedom. So you want to be able to design it. You need the tools to be able to solve this indirect problem, which basically is given a certain platform and a certain mission, you want to obtain what is the best propulsion technology that actually allows you to fulfill the mission in the best way. So our solution is NA Space Software Suite, which contains two complementary tools for end-to-end mission design, in particular for the optimization of propulsion, modular propulsion technologies, which are called YANEGO and YANE360. So I'm going to spend a couple of words on YANEGO very quickly, and then I'm going to focus on YANE360. So YANEGO, as we call it, Rocket Design as a Service, is a tool for concurrent maneuver and propulsion system design optimization, which it follows a simplified approach based on secular motion So it's suitable for preliminary analysis, preliminary optimization of both trajectory and propulsion. Is an open access tool, so it's free for the community, is very user-friendly, very fast and robust. And we also benchmarked it against GMAT. So just to give you a feel of what Yenego is, this is a screen from the actual tool. You can see this is the setup pane in which you have the platform selection. Then you can set some thruster constraint for which are going to then drive of course, the design and some initial features for the orbits. And this is the mission scenario selection, in which you can select several maneuvers and compose your mission, and of course, input the various specific maneuver inputs and constraints. And the typical output that you get from Yenego is, for a particular example that you can see on the left, is this kind of pentagon-shaped graph in which you see let's say, a summary of all the main interesting things for each maneuver that you're performing. So the delta V, the thrusting time, the power of the thruster, the total impulse. But most interesting, you get a design for the thruster. So this is a design that we obtained for this specific mission using Yenego, and with all the main information such as the mass, the volume, the power, and the ISP. So that's it for Yenego. The beta is available now, it's open, and you can register for free at go.yen.space. If you have any questions about Yenego, you can contact my colleague Borja de Saavedra. So now I'm gonna switch to Yen 360. I'm gonna focus on this tool that I am developing. And so Yenego is, as I said, a tool for preliminary analysis. It's based on a simplified approach, which makes it very rapid. But we wanted to be able to cover the full spectrum of mission design. And that's why we conceived Yen 360, which is a tool for detailed analysis, for high fidelity optimization, and is not only oriented towards design of the and optimization of the system, but also to operations. So here you see the architecture of Yen 360. The core is a maneuver optimizer, which contains a high fidelity propagator and an optimizer, which is based on the kilo algorithm. This is wrapped in a heuristic solver, so basically a genetic algorithm that allows us to solve multi-objective constrained hybrid optimal problems. This is the choice of the genetic algorithm is driven by the fact that there is no need for initial condition. It searches for global optima as opposed to gradient-based solvers. Of course, as a drawback of requiring a lot of function evaluations, so it's not very fast. And that's why we run it inside of a cloud computing platform, which allows us to parallelize the processes and boost significantly the computational speed. A bit more in depth, so Yen 360 is a high fidelity tool, as I said. We propagate the full equations of motion. You can see an example of the orbital elements, and you can see the typical oscillations given by highly perturbed orbits. And we have several models for the perturbations that you can tune depending on your, let's say, level of the phase of the mission in which you're designing the mission. So more simplified models against more complex and time-consuming models, both for gravity, atmospheric drag, and other perturbations. And then another feature of Yen 360 is that we're using a model-based approach. So everything in Yen 360 as a model. For instance, the thruster as a very complex model, of course, because it's what we're trying to optimize. And at the moment, we have a model for our Athena thruster with the which is a fit of the current data that we have and the expected performance. But we're planning on adding also other propulsion technologies. Then we have models for the subsystems, in particular for the EPS, the electrical power system, and the attitude and determination control system. This is critical if you having good models for these subsystems, if you want to perform a concurrent engineering approach, and if you want to be able to enforce complex constraints in the design and in the optimization of your propulsion system. Additionally, we also have, of course, events such as eclipses, visibility operations, which all concurs in the enforcement of complex constraints in the problem. In this graph on the left, for instance, you can see the power generation profile. As you can see, it's very, very complex, very realistic. Again, because we have these models, these detailed models, and same for the power consumption. You see this complex modeling. So Now, for the rest of the presentation, I'm going to show the same maneuver, which is a change of semi-major axis eccentricity and inclination. But I'm going to start, let's say, simple and then increase complexity as I proceed in the presentation. And I'm going to be considering a 3-unit CubeSat and powered by an Athena thruster. For the very first examples, I'm going to consider the 3-unit with body fixed solar panels with a certain battery configuration and certain subsystem configuration. And the Athena, again, in the first examples, is going to have a fixed configuration, so 6 stacks and 10 watts. But then we're going to allow for the design of the thruster, and you will see that this will change. So this is an overview of the algorithm. There are some inputs, which are the ones I described in the previous slide, basically. And now, in this first example, I'm going to be using just the core, so the maneuver optimizer, which now is a bit more detailed. You can see that it contains the propagator and the optimizer that is in sort of in a feedback loop with the optimizer, with the propagator, I'm sorry. And the maneuver optimizer basically produces an optimal maneuver, a single optimal maneuver, which has these features, so a maneuver duration, a propeller necessary, the guidance laws that you can actually input on your ADCS to perform the maneuver in real life. So just to clarify a bit what the optimizer does, in principle, it computes the optimal thrusting angles to minimize the transfer duration. Now here you have, to give you a reference of what I mean with thrusting angles in the radial circumferential normal frame. Anyways, in the propagation step, at each step, the optimizer computes these thrusting angles, and so you get this kind of profiles, which then, of course, translates into the change of the orbital elements. Additionally, this optimizer is also capable of computing whether it's better to perform a thrusting arc or a coasting arc through a parameter which is called thrust effectiveness, which is based basically on the orbital energy. So now I'm going to increase the complexity. I'm going to turn on the genetic algorithm, as you can see here, and I'm going to basically allow the genetic algorithm to tune the weights of the optimizer and this coasting parameter. And I'm going to set 2 objectives. So we're going to try to minimize 2 things, which are the maneuver duration and the propeller necessary. So now we're not going to obtain anymore a single solution as in the previous case, but now we're going to get a set of solutions. So we get something like this when we run the genetic algorithm, a lot of iterations. But I would like you to focus your attention for a second on for instance, on the 20 days solutions. If we see that there are several solutions, but one minimizes also the propellant mass. So all the solutions that have this feature are eligible to be part of the Pareto front, which is basically a collection of the optimal solutions with respect to multi-objective problems. So in particular, each of these points now represent a different maneuver. So for instance, the point A represents the shortest maneuver, but also the most expensive. And you can see that the thruster is firing continuously and the maneuver ends after about 12 days. While the point B represents the longest maneuver, but also the most fuel efficient, because the genetic algorithm is making the optimizer fire only when it's really the most effective. Of course, this introduces coasting arcs and makes the maneuver much longer. And this is an idea to give you an idea of the duty cycle. So now I'm going to actually allow the genetic algorithm to receive as inputs the thruster model. And this will allow to actually design the thruster, and in particular to tune the power level of the thruster and the number of stacks, while at the same time still optimizing the maneuver. So just to clarify, when I talk about power, we can increase the power by increasing the grid voltage. And when we increase the grid voltage with the current model that we have an increase of both thrust and ISP. So we obtain something like this. Now, these cyan solutions were the 10 watt 6 stacks fixed solution for Athena. But now we have this new Pareto front, which, as you can see, is much more optimal. So the previous case, again, is suboptimal, so we get rid of it. And now let's analyze a bit these solutions. What we find, first of all, is that there is a discretization of the number of stacks. Here I was iterating between 2, 4, 6, and 8 solutions, and we obtained 2 families of solutions, one with 8 and one with 6, which you can recognize here. And also another interesting thing is that all of these solutions are at the maximum power. And this is because, as I said before, when we increase the power, we increase the voltage, and hence we maximize the thrust and the ISP per configuration. Also, we noticed that the 8 stacks solution prevails in the short maneuvers, and that's because for the same voltage, and they have the same voltage, we have more stacks, so we produce more thrust, but we have the same ISP. So now I'm gonna increase the complexity even further. In particular, I'm gonna add a constraint in the problem, in particular, a constraint on the battery. In this case, basically, if the state of charge of the battery goes below 70%, we shut off the thruster. And when the battery replenishes, we allow for restarting the thrusting phase. So this was the previous solution. And now with the constraint, we obtain this kind of Pareto form. So these are all the optimal solutions that we obtain. And as you can see, first of all, we see that we lost all the short maneuvers because in principle, the short maneuvers have long thrusting arcs, but we are not able anymore to sustain long thrusting arcs because of the constraints. So there is a premature shuts off of the thruster. And that's why we lose all these solutions. Also, we noticed that on the right, the long maneuvers are exactly the same. The solution that we obtained are exactly the same as the unconstrained case. And also, we noticed some interesting solutions here in which the thruster, the genetic algorithm tries to reduce the power of the thruster, but to balance that power, that constraint on the battery. But this also means reducing the performance of the thruster. So you see that the points go up in terms of propellant mass since we're decreasing the ISP.
We've got 1 minute left, Giuseppe.
Okay, sure. So just the last example. Here, we're going to allow for concurrent optimization of the thruster, the maneuver, but also the power system. And we're adding another objective, in this case, which is the system mass. So now we have 3 objectives that we're trying to minimize. And in particular, I'm going to be iterating these configurations for the batteries, so a smaller and a bigger solution, and then 3 configurations for the solar panels. And we obtain something like this. This is a 3D Pareto front. It's a bit harder to read, but it's interesting to notice that we have 3 different stack configurations. All the configurations are at the maximum power, so the maximum voltage. The small battery, it's predominant, and we have only one solution with the bigger capacity. And we also recognize the impact on the system mass of the solar panels configurations. Well, this is the same graph, but projected. And you can see also that if we have bigger solar panels, let's say, we can also obtain maneuvers that are shorter. So we have more power available. So I'm just gonna conclude here with some closing remarks. So EN360 is a tool that we designed for optimization of Athena, but we want to have a tool that allows designers to perform informed decision between a lot of optimal solutions. At the moment, the tool is internal, but we are planning for its future, and we're open for 2 collaborations. And we want to improve it much more. We want to improve the models, so the realism. We want to explore variable operational maneuvers and the robust optimization and operations. So that's it for me. Thank you. And if you have any question, now we'll be taking them for both our talks, as we said at the beginning.
Thanks a lot, Giuseppe. Thanks a lot, Sarah. Wow, I really found it impressive, the 2 of them, huh? Thruster side and software side. So we have time for questions from the audience. I don't see any at the moment, but I will start. I have questions for the 2 of you. Sarah, I just noticed that in your efficiency equation, there is a square for the transparency efficiency. It's because you have 2 grids.
No, it's not because we have 2 grids. Actually, when you derive all the equations, transparency efficiency appears to the square. In this, okay. You can, I could send you the reference.
I have to do the exercise. It's a good exercise for me and my students anyway. Okay, so
it's not because
the fact that you use 2 grids. Okay, and I was wondering, probably you mentioned it, but what is the size of the square thruster, the small unit, the smallest unit that you have? What is the size?
The size of what we call the active area, which is where we have all the emitters, is 10 times 10 square millimeters. So it's 1 centimeter, 1 centimeter square. Which is that is the size of the active area. On this version that I have presented here, we are moving to actually to a 2 centimeter square of active area. So we are moving to a little bit larger and more dense emitter now.
Okay. And a quick question to Giuseppe, because we have questions from the audience. Giuseppe, do you plan to have at the end a student version also? It could be very useful for us when we are teaching, to be able to use the software to show the student that depending on how you design your thruster, you will change the parameters and then you have to find the optimization.
Yeah, that's a good question. I mean, as I said, this is at the moment an internal tool that we have. We're still developing.
Of course.
So we're still looking into the future of the tool and see how we're going to, let's say, bring it to the industry. But again, Yenego is let's say a simplified version, but it's free. You can try it. It's very user friendly, and yeah, it's go.yene.space on the website. You can just register.
Okay, I will try. It could be very useful when. Okay, so now we have a question from Timothy from the audience. So Timothy, you can ask a question.
I think that's me. It's a typo on my name. I'm Shadrach Hepner. Thank you both for these talks. This was very interesting stuff. I had a question regarding the efficiency number, the thruster efficiency numbers presented. Unless I was misunderstanding, it looked like the 70% or so number was primarily for a very low power operating condition. I think I saw a third of a watt or so. So I wanted to ask how you all expect that this number might scale as you bring the test to higher powers, such as tens of watts that were presented in the software talk.
Yeah, thank you, Timothy, for your question. Yes, the numbers that I presented here, when we computed the efficiency, was directly with the thrust measurements. It was with a very low power operation. It was just one chip and one chip that was being used for a long time. So this chip was actually 0.32 watts, which is quite very low. But still it's very high efficiency. What we expect when we go to higher powers, normally the efficiency of the thruster will remain almost the same, like with these very high numbers. What will probably increase also is the efficiency of the PPU, also at higher powers. But one of the biggest advantages of precisely the electrospray technology is that when you scale down, you don't lose this efficiency because it's not a plasma thruster itself. So this you don't need to account for wall losses or for thermal losses. This is not something that you need to take into account. So you remain with very high efficiencies from very low powers to very high powers. So yeah, nowadays we are like the highest power we are aiming with our first developments is 100 watts. So we expect to develop a 100 watts thruster soon.
I see. Thank you.
We have another question from Christophe Coppel from the audience. Christophe.
Hello, Sarah. Thank you for your presentation, and Giuseppe too. I have a question about. Okay, you have a large number of small emitters. 100, you say, and you want to go to 385. I would like to know if all the emitters are working, and how do you know that? Because, okay, come on.
Yeah, no, that is actually a very good question. Now, at the moment, we don't know how many emitters are working, okay? But we are developing a diagnostic that we will develop. One of my colleagues is working on that full time. We'll develop next year. It's a tomography system. So with tomography, you can actually see and how when you do the you point tomography to the active area and you cover all the active area, and you can actually see like these light points, and you can then you can post-process and more or less see how many emitters and which emitters were actually emitting current and not. But this is actually a very good question. It is one of uncertainty that we have at the moment. One thing that we can do, and what we normally do, is once after the thruster has been operating, we inspect the thruster under the microscope, and you can see at least how many emitters are actually wet. So this is not, obviously, it's not 100%, you cannot be 100% sure that they were emitting, but at least you can see that how many emitters were actually wet. So this is the thing that we are doing at the moment. It's a very good question, and definitely we are working on developing the diagnostics to be able to characterize this.
Okay, thank you for this answer. Very good. Second one to Giuseppe is, okay, with your tool, do you manage also the attitude control effects? Because
Yes.
if you have not in line with the thrust in line with the center of mass, you have always talks. So did you manage that, and what should be what would be the result in terms of propellant mass in each of your 6 or 8 thrusters?
Yes, absolutely. That's a great question. In fact, that was one of the last points. That's basically robust optimization, because now you're talking about that loss that you have due to the off center, but in reality you have a lot of uncertainties. You have also the trust that you're getting is not always precisely what you think. So in the optimization process, we're going to include basically all these uncertainties, which then will end up in solutions that are, of course, a bit less optimal than what you get with the optimized case, in which we are not really seeing all these effects. So this is something that we're implementing in the future. It's already in the plans in terms of this robust optimization. Okay, but about attitude control, you use a thruster to do that, or you use something else like a magneto-torque? Yeah. At the moment, is not the thruster that is producing; it's doing the attitude control. But could be possible again thanks to the modular approach. As you've seen, we have different stacks. So in principle, you could do at least a 2 degrees of freedom of attitude control. But for the moment, we're not exploring that. So in the future, I think we're gonna go in that direction, because it's very nice to have an integrated system that is capable of doing both propulsion and at least a limited amount of attitude control. Okay, if you have some angle between your thruster, you can have the 3 degrees of freedom, you know. Yeah. Okay. Thank you. Bye-bye.
Thanks a lot, Christophe. So thanks again to Sarah and Giuseppe for this very interesting presentation by NIA Space. So now it's time to switch to the second invited lecture of this morning. So the lecture talk will be given by Naomi de Mejan. Naomi, are you there?
Yes, I'm there. Hello.
Okay, great. So the talk will be about interaction between the plasma and antennas, which is extremely important for our community, and it's becoming more and more important. So that's why we invited you. I think this is the first time we have this type of communication in this workshop, but I think it's very important for our community. So Naomi, you will have 30 minutes, and again 10 minutes after your talk.
I thought it was 15 minutes.
What did I
presentation
say? No, it's half an hour.
Okay, but
that means, Naomi, that you will have more time for questions, which is very good also.
Okay, great.
At the end. So you have plenty of time. Okay, so I leave.
Okay. Just do you see my screen? It's okay?
Yes, it is.
Okay, thank you. So good morning, everyone. My name is Naomi de Mejan. I am a PhD student at ISAE Super-Aero in Toulouse. My PhD is funded by the CNES and ISAE Super-Aero. I am supervised by Romain Pasco and Olivier Pascal, with the participation of Laurent Garrigue, Vincent Lakerbe, and Alberto Rossi. And I am glad to be here to present you our work about the interaction between microwave antennas and the plume of a Hall thruster integrated on a small spacecraft. So around the 2000s, the emergence of a new standard, the CubeSat, allowed the development of low-cost and public access to space. The reduction in cost was made possible, in particular, thanks to the reduction in the mass of the platforms. For this purpose, the satellites have been miniaturized, and the thrusters too. So in this context, electric propulsion is preferred to chemical. And even if electric propulsion technologies have been validated for large platforms for years, miniaturization has imposed new constraints in terms of performance and power available, price, mass, volume, and finally, what I'm concerned with, the electromagnetic compatibility, that is to say, the ability of an electrical system to function in its electromagnetic environment. So in our case, we are dealing with the electromagnetic compatibility between the plume from the propulsion system and the microwave communication system. So the microwave communication system relies on antennas that can operate between 100 megahertz and 10 gigahertz to ensure, for example, positioning, telemetry, or telecontrol. But unfortunately, the plume is an electromagnetic complex medium that may modify the closed environment of the antennas and disrupt that functioning. So before saying how the plume can actually disrupt the proper functioning of an antenna, what is the proper functioning of an antenna and how can we estimate its required performance? So to qualify the performance of an antenna within a communication link, we'll use the signal-to-noise ratio at the receiving antenna output. The signal-to-noise ratio, or SNR, is the ratio between the power of the useful signal and the power of the received and inherent noise. So as shown on the right here by the Friis equation in free space, the received signal power S at the receiving antenna output depends on the transmitter power in, P in, the wavelength lambda of the signal and the distance R between the transmitting and receiving antennas. And finally, a quantity called the antenna gain. The gain of an antenna is the angular distribution of the radiated energy that takes into account the losses of the antenna system, and it depends on its environment and can be perturbed for any conductive or refracting element in its vicinity, like our plume, for instance. So, how the plume can disrupt the proper functioning of the microwave communication system? First, in the plume, there are complex physical processes that can lead to electromagnetic radiation in the bandwidth of the receivers. But from the point of view of the receiving antennas, these radiations behave as a noise source. Also, the plume can modify the propagation channel. Indeed, its permittivity is not that of vacuum, so the environment in its vicinity of the antenna can be modified, resulting in a change in its gain pattern and thus its received signal power S. So this specific point is the subject of my PhD, and I will now present you a method that we have developed to address this special issue. So what are the ways to answer the question of electromagnetic compatibility between plasma thrusters and the microwave communication system? First, the best way will be to ensure compatibility in flight by developing a mission specifically for this purpose, but it's very expensive and the development time is very long. The CNES is currently working on such a mission within the C3PO program. Alternatively, we can measure the thruster antenna compatibility on the ground in huge vacuum chambers, but these experiments are also expensive and pose some challenges, such as the residual pressure in the chamber, the modification of the shape of the plume due to the presence of the walls, and of course, the fact that the measurement of the electromagnetic radiation is complex in these conditions. Finally, we can try to answer this question numerically. This way, add the interest to be low cost, but the modeling of the multi-scale physics remain complex. Anyways, whatever the method chosen in the past, compatibility has only been studied for large platforms, and it was concluded that the satellites should be designed to prevent the electromagnetic wave emitted by the antenna to cross the plasma plumes. For example, as you can see here in the Eutelsat 172b picture on the left, the thrusters at the end of the telescopic arms are located are located opposite to the communication system. This satellite measuring more than 5 meters, it was possible to physically separate these two subsystems. Now let's have a look at a 6U nanosatellite. It's clear for this kind of small platform that the thruster and the antennas can never be separated in a such way. That is why it seems necessary to ask this question of their compatibility in a context of miniaturization. And in this aim, we propose a numerical method to study the interaction between microwave antennas and the plume of our thruster integrated on small spacecraft. In summary, the objective is to use a plume model to describe the plume as a dispersive and inhomogeneous material represented by its permittivity in an electromagnetic simulation software. But let's first have a look at the simulation of the plume. For this, we use a Jet2D, which is an hybrid plasma jet model of a thruster developed by Laurent Garing from the Laplace Laboratory. This code allows us, among other things, to obtain the local electron density within the plume. This is what we see on the right, namely the distribution of the electron density in a two-dimensional half plane. This code was originally developed and experimentally validated for standard SPT 100 type Hall thruster. So there was a need to adapt the input parameters to approach the conditions of a representative plume of a micropropulsion Hall thruster. So this is what we see at the bottom right. We have searched for the Jet2D parameters to have the best agreement between the simulated and the measured current density. So here by Thibaut Allouin and Stéphane Mazoufre in the plume of a 100 watt class Hall thruster. Now, in order to represent the plume by its local permittivity in the electromagnetic software, we use the Drude model. The Drude model allows us to obtain from the local electron density distribution the equivalent local relative permittivity, epsilon. So being a dispersive medium, the permittivity is also a function of the frequency of the electromagnetic wave passing through. And you can note that the Drude model is also a function of the neutral electron collision frequency, which is in our case much lower than the frequency of the microwave signal. So at the bottom of the slide, you can see the translation from the electron density to the real part of the permittivity. For here, a microwave frequency of 436 megahertz. So you can see in particular in the H part, which corresponds to the zone of negative permittivity. That is to say, the zone where there is no propagation of the wave. This array is quite small, namely less than 20 centimeters long in these conditions. Now we want to represent the plume as a discrete three-dimensional material in the electromagnetic solver where the whole problem will be represented. To do so, we decided to use ANSYS HFSS, which is a commercial software that solves time harmonic Maxwell's equation using finite element method. So first we have to choose the platform we want. Here, for the example, we have chosen a 6U nanosatellite. Then you have to choose the antenna you want to simulate. Here we have considered a dipole antenna that operates in the UHF band at 436 megahertz, which is used for telecontrol. And for example, we put it in the middle of the upper side of the platform. Finally, we have to represent the plume. To do so, thanks to a script, we realize the assembly of toroidal materials of defined permittivity coming from the Drude model. This is what we see on the right, the construction of the plume, and finally we get something like this. So to build and define the plume, you have several choices to make. For example, the operating condition of the thruster, which can modify the density or the shape of the plume. The integration of the thruster, that is to say where you will choose to put the plume on the platform. Here we have considered that the exit plane of the thruster is on the bottom side. And then you have numerical choices to make, like the spatial resolution, which is the size of the section of a toroid. This choice is motivated on one hand by the frequency of the propagating microwave, because to represent the interaction correctly, this length must be much smaller than the wavelength, but also it is necessary to be able to limit the computational time. So we must not choose a spatial resolution too small. Also, we have to choose the limit permittivity, epsilon max, which is equal here to 0.95. This limit permittivity represents the limit between what we consider to be the plume and the vacuum. The goal is also to limit the computational time, because the more elements to simulate, the longer it takes. But we still need to represent correctly the problem, and that these choices does not influence the results. So this is a kind of results we can obtain. On the right, you can see the gain of the antenna here, a microwave, a UHF dipole. The gain antenna, I remind you, is a distribution of the radiated energy. Here, the gain is represented in 2 dimensions as a function of the theta angle in the plane defined on the left. The dotted curve represents the off condition, and the solid curve when the thruster is on. We see distortion of the gain, especially in the area where the plume is located. That is to say, around theta equal to 180 degrees. And if we look at the total radiated power, we observe that it's quite the same before the on and off condition. And this small loss is explained by the low collisional nature of the plume. And so we can infer that the change in the antenna gain is mainly due to the permittivity gradient of the plume. The method we propose allows, among other things, to test several integration conditions of the thruster or the antennas. So here we look at the effect of the plume position on the antenna gain. On the right, we can see the distribution of the gain in space when the thruster is off. The green area corresponds to a zone where the gain value is higher than the maximum gain value minus 3 decibel. We suppose that it is the area covered by the antenna. And when the thruster is switched on, for example, here under the platform, we can see a slight distortion of the area within, in particular, a loss of coverage in the lower area where the plume is located. If we now simulate a case where the plume is on the side face, we get this gain distribution. We still observe modification, but this time the modified coverage area is located on the side of the antenna, once again where the plume is located. And finally, a case where the thruster is on the upper side of the platform. So once again, we observe a modification of the coverage area, especially here in the upper zone where the plume is located. So from these 3 cases, we can say that change in the radiated power distribution depends on the relative position of the antenna and the plume, and also that the modifications are the most important in the area where the plume is located. To conclude, we have developed here a methodology in order to estimate the interaction between microwave antennas and the plume integrated on a simplified CubeSat. This method is versatile and allows us to test many cases. This method is easy to implement as long as the electron density distribution in the plume is known. And future work will consist in validating this method by benchmarking it with our partners and by developing a ground experiment to obtain some measurements. So thank you for your attention, and that's the end.
Thanks a lot, Naomi. I think it was very interesting. And as I said already at the beginning, it's very important for our community to be able to infer the disturbance that our thruster generates in terms of communication or GPS signal or whatever. I have check a question from the audience. But at least, yes, we have a question from Christophe Theroux from Airbus. Christophe, you can talk. Christophe, your microphone is open, so it should be okay. We don't hear you. So we have a problem with Christophe, the communication with Christophe. So there's no thruster on. I just have a question. When you shown at the end this 2D plot where you were investigating the disturbance created by the plasma, so with the green background, saying that's where the gain is max, and you clearly see small disturbances in some, at least what I think is small, very small area were affected. So now for us, the question would be, so finally, do we disturb or not the communication? Can we operate the thruster without, I would say, too many impact? I think for our community, it's very difficult to interpret your diagram.
Yes, but for us too, because it will depend on the mission and what you want. And I remind you that this result was shown for a special condition here with all thruster with this operating conditions. But okay, here it seems that the disturbance is slight, and once again, I don't know what slight disturbance is for the people who work. But in other conditions, like for another thruster, for example, arc thruster, it could be more powerful, or there would maybe there is more density, and maybe the shape of the plume is not the same. So we can conclude on the real disturbance of all the thrusters in all the operating condition, but we try to develop a method to study this question and to test many cases.
Yeah. If I can add a comment also, Naomi, you show as you said, one specific condition for the thruster, but you have also checked for one frequency.
Yes.
Yes. So maybe it depends also what kind of communication and what is the frequency also of the communication you need for your missions. Obviously. Okay. So that was one test for one frequency for the antenna. You know. So obviously it depends also of the omega. Of the wave frequency of the antenna also.
So Christophe. Strange because the microphone for Christophe is open, can you access the question of Christophe now? If not, it's in the
yes.
So okay. Just for the audience, the first one is Christophe is saying that you perform the simulation for a whole thruster that is firing continuously, but can you include pulse mode operation in the model? And the second question is that you perform simulation assuming that the density of electron is constant. Why it probably in time? I mean, why it's not the case? So also include the impact of the fluctuation of the plasma.
Yes. So with our method, we can't do this because we're using an electromagnetic software, which is here ANSYS HFSS, and it resolves time harmonic Maxwell's equation that imply that it's a stationary regime. So it doesn't permit to study the variation in time. But it's a really good question, and it will be great to study this time varying effect.
So that also means that you cannot take into account the plasma fluctuation, but you can also simulate pulse operation of thruster, right? Have any time variation in your model?
No.
Okay. Are there any other questions from the audience? I don't see. Yes, Jacek. Should be able to give you. Well, Jacek, ask a question. Marlene, I cannot open the microphone of Jacek. But Marlene is not here. Jacek, if you hear me, can you just write down your question? Because for some mysterious reason, I cannot open your.
It's okay now, you can.
Oh. Okay, your microphone is open. So you can ask your question yourself.
Okay, thank you very much. Well, it's very interesting talk, but I just wonder if it would be possible to screen somehow plume with respect to the own antennas. Well, because for microthruster, the size of plume seems to be tiny. So I just wonder, with using any kind of foils, for instance, metallic foils or something like this, with a construction, or I don't know exactly, like inverted umbrella or something similar. If it would be possible, what is your opinion? It's just comment, nothing more.
I'm not sure what you're saying by tiny plume. How can you say that the plume is tiny? Because with the information that we have, the plume is not so tiny. Okay, maybe visually the emitted light is in the small zone, but from the electromagnetic point of view, the plume is not so tiny.
Okay, well, I don't know exactly what is the influence. So it perhaps it's result of your calculation, how big this plume and how important size of plume is for this electromagnetic noise, but doesn't matter. Well, my question is if it would be possible to apply any kind of screening.
Of what? Of what? Sorry.
Of screen. So can you reduce the size of the plume or the interaction if you use a screen, like a piece of?
Ah, okay.
If I understand well the question of Jacek.
I don't know at all. I don't know.
But this could be simulated, right?
Maybe I don't simulate the plume.
But I mean you. Oh, that's true.
The software I use not simulate that kind of interaction. So
yeah, the plume is the input data for you, but
okay. Yes. No. We could yes put a screen around the thruster exit. Okay. Yes. I imagine we could do this. Yes.
May I add a comment? I don't know if you hear me.
Yeah, Romain, we hear you.
Thank you. I'm supervising the work of Naomi. Just add a thing regarding this question. I think, yes, we can think about a new way to kind of reduce the interaction between the plume and the antenna. However, for the antenna engineers, adding some foils, adding some metallic parts means that you will have to redesign your system to have the same coverage, because if it is not the plume that is interacting with the radiation, it will be the foil. So the question is, of course, we will hope that we will coexist on the same platform, but we have to find solution altogether, because antenna engineer also will have problem in adding structures, metallic structures close to their radiation pattern and so on. So right now, we didn't think about the solution. We more think about, is there a problem? Okay, maybe they're not. And the first result for the case we study the impact was not that large, but we cannot be conclusive yet because you have different operating mode, you have different type of antennas. Here we didn't speak also about the polarization effect because in fact the plume behave as a spatially variant dielectric medium with a gradient. And so you have kind of a lens effect. So these lens effects tend to change the direction of the radiated waves, but also can change a little bit the polarization of the waves. And if you think about GPS antennas and so on, they rely on this polarization. So we have a lot to invest right now on that topic. We have started the PhD of Naomi 2 years ago. So we are already pleased to see how to handle part of the problem, but I cannot say that we have conclusion yet. And just concerning the question of the time varying effect of the plume, maybe we can deal with that with our solution now by solving different state of the plume. I mean, different density and doing like a transformation from the harmonic, because we can perform broadband simulation and then we can do inverse Fourier transform to go back to the time domain and maybe have a look at by compiling simulation from different plume model. But we didn't think about it yet. And maybe a better solution would be not to use a time harmonic solution like HFSS, but maybe a finite difference time domain methods where we can try to, but the time scale will be quite difficult to manage, to change the plume density at the time scale of the plasma evolution and to look at the microwave effect. But the thing is that the time scales are very large, very different. And so we need to handle this difference in time scales in a finite difference time domain method. But it could be something to look at because in time domain, in a classical FDTD method, we have a cubic cells and we can put some permittivity in the cubic cells and make them evolve in the time domain, for example.
I see. Is it a kind of, it's a new area of investigation, right? This interaction between the plasma and the communication system?
For us, kind of, but if you look to the literature, you find some things like that, not dealing with plasma thruster and so on, but more on rocket thruster, the impact of the rocket plume on such things. You have some works that have been done numerically. You also have some work dealing with a blackout effect.
Mm-hmm.
Each vehicle is coming back and you see that you have a plasma around your antennas. So you have some works dealing with that. But the question of plasma thrusters and communication systems has been looked at for large structures, but the conclusion were do your best to put them very far one from each other. Okay. On small spacecraft, this conclusion is not possible anymore. So we have to look at it one more time and maybe we will find that it's not a big deal, but I think it is important for both communities to be sure that we can be neighbors on the platform.
Are you aware of any report about perturbation of communication already observed in the real life in space with small satellites?
I'm not.
Me neither, but it's not really. So, there was an interesting remark from Christophe. I think Christophe was talking about a shield or a screen that if you add a structure, you will also have to deal with erosion and sputtering and wear of the structure itself due to interaction with the ions from the jet from the beam of the thruster. That's true. My feeling is that if you add, so I'm not thinking about the fact that the screen will interact with the communication system, but also it's also complicated for us because it will also interact with the ion beam of the thruster. So this is a bit tricky, and it will make the entire system more complicated at the end. So, but it's interesting to see if it's an interesting solution or not. Are there any other further questions from the audience? We still have a bit of time. No, I don't see. I don't see. Christophe. Christophe, yes.
Okay, c'est Christophe Coppel. It's not Christophe Theroud.
We see your name on the screen, so that's fine.
Okay. Just a question. On my work, I was using the interference with a phase shift between the the plume or the phase shift into the plume. So your work is not related to that.
I'm not sure I understand the question.
If you want to know me, I can answer because
Yes.
I get it. Yes, of course. Deviation pattern that Naomi has plotted only show the magnitude of the gain. Can also be viewed. It's a complex figure that has a phase, and clearly the phase is also an important parameter for us, especially if you think about synchronization of the system, because if you have a time varying plume and so time varying phase shifts, we can expect, and it has been seen for interaction between rocket plumes and antennas, that you can unlock the phase locked loop of the receivers. And so, for example, in a GNSS application, a GPS application, where you try to be locked all the time to have a good positioning, if you unlock when you turn on the stressor, you will have a problem in computing your position. So, of course, you have both effects, effect in the amplitude pattern, what Naomi has shown, but also on the phase. And since we are at the starting point right now, we cannot conclude yet. But when you deal with communication system, of course, you have the magnitude, which is important also, but the synchronization implies that the phase shift is not evolving that much of the carrier frequency. And if it is the case due to the plume, it will also be another problem. And finally, but last but not least, as Naomi mentioned, the noise generated by the plasma itself also can be a problem. And you find some works in the literature where you see that the noise floor producing by turning on the thruster is increasing, and especially in the bands we are interested on. And so this question is also critical, because if the noise floor of the receiver is going up, then you have less sensitivity to detect your useful signal, and then you can lose the link. So we find Naomi just worked on one part of the problem, but from my point of view, the problem is very large and needs to involve more, maybe persons, more activities to be sure that the plume or the thruster is not a problem for the communication system.
Okay, just to remember, the density of the plasma is also the main input to compute the phase shift, of course.
Yeah, no, Mia, you should.
Yes. Yes, we for the Jude model, yes, the electron density is finally the only input with the electron neutral collision frequency, but that the only input obviously with the frequency for the permittivity, but the electron density depends on the input of the Jet2D code, which are current, specific impulse, temperature, and other things.
Thank you.
Thank you, Christophe. Are there any other questions before we go for a break? I have a last one, Naomi. It's about the Druid model that you are using. Why did you choose the Druid model? Probably because it's simple. And are there any other model that could be used?
We choose a Druid model because it's a simple way to represent the plasma as a material in an electromagnetic solver. But I don't know if you could use other model to represent the plasma. Actually, in the plasma wave interaction problem, what is used is often the Druid model.
Okay.
Well, but if I can just add a last comment, clearly,
yes.
We are dealing in Toulouse in different application of plasma and microwave interaction, not only that one. And typically, sometimes we are wondering if the Druid model is accurate enough to represent all the interaction that can happen in such a low pressure plasma. Because maybe you can have electrode to acoustic wave conversion. You have some things that the Joule model is not representing.
Sure.
Yeah, so the question is it always, are we sure that the Joule model is the best representation? But for us right now, it's the simplest way to look at the problem. But we need the measurement data to be sure that the model is correct, the methodology is correct, and that we can use this type of methodology to go further. So we will try to do our best to have some measurements, but it's not easy.
Thanks a lot, Romain, for this comment.
You're welcome.
Okay, so I think we are perfectly on time, which is great. Thanks a lot again to all the morning speakers, Sarah, Giuseppe, and Naomi. Thanks for your talks there and your presentation. It was very interesting, very new. I think the community learned a lot. So now it's time for a short break. So we have a 20-minute break. Okay, we will meet again at 11 p.m. For the second part of this morning session, and the session will be chaired by Laurent Garrigue at 11 o'clock. Okay, enjoy your coffee break. We meet in 20 minutes.
Stéphane?
Oui, Laurent.
Ouais, tu me rends la main ou c'est...
Non, je te rends la main.
Ah oui, je pensais qu'elle avait pris Marlène, d'accord.
Attends, c'est pas plus. Hein. Non.
Il faut l'animateur. C'est dans plus et plus mon nom.
Comme animateur.
Ouais, c'est ça.
Okay.
Ouais, c'est ça. Bon, ben c'était bien, tout ça.
Normalement, c'est bon, hein, t'es passé.
Ouais, c'est bon, animateur, c'est bon.
Okay.
Ouais, j'ai eu l'élection passée, c'était bien.
Ouais. Écoute, tout était bien. Je pense que c'était très, très bien d'avoir cette présentation.
Ouais, je t'avais dit, non, c'était bien. C'est nouveau,
Vincent, Naomi.
C'est nouveau, ouais, c'est assez nouveau. Et c'est vrai qu'il y a plein de choses à faire là sur la partie, sur ces parties-là, quoi. Et notamment, voilà, donc elle a regardé. Donc, en fait, il peut y avoir un problème d'Android si tu vois, nu tend vers oméga, quoi. Parce que 1 moins racine, tu vois, il y a 1 moins c'est là, c'est un problème. Parce que tu peux avoir des modes de couplage, type anormaux, enfin des choses super compliquées.
Ouais.
Mais alors là,
il est vraiment simple.
Ouais. Après, ça marche. Ouais, la plupart du temps, c'est pas mal, quoi. Du moins pour un premier test, c'est vraiment pas mal, quoi. Après, voilà, ça dépend aussi de la fréquence, tu sais, que tu prends pour l'onde, bien sûr, le nu sur oméga, quoi. C'est ça qui est important. C'est ça qui fait une absorption ou pas, quoi, finalement, au milieu. Et on a la chance, finalement, nous, on a la chance quelque part d'être vraiment en expansion. Et dans le nu, il chute, il n'y a plus beaucoup de gaz.
Ça va vite, hein. Ça va,
si tout va bien. Si tu as bien ionisé ton gaz. Si tu as bien ionisé ton gaz, tu vois, le nu, donc voilà, c'est pour ça qu'on aurait nu qui tendrait vers oméga, alors là, tu as de l'absorption, et alors là, par contre, ça peut être un gros problème, tu vois.
Parce que l'impression que j'ai quand je regarde le travail, ce qu'a présenté Naomi, ce que fait Claire, l'étudiante que je supervise qui travaille avec eux, hein, c'est que j'ai pas l'impression que ça perd tout, mais c'est un feeling.
Ouais, alors après, voilà, mais je me dis quand même que même sur les moteurs classiques, elle a montré, et c'est bien qu'elle ait trouvé le Telstat. Moi, je n'arrivais pas à trouver l'antenne déportée. Je ne trouvais pas mais bon, je pense que c'est pour d'autres aspects. Mais c'est vrai qu'ils avaient mis vraiment l'antenne à l'opposé. Et pourtant, c'est pareil, ils sont à 5 mètres. Bon, a priori, tu pourrais te dire que. Mais ils prennent tellement de marge, je pense, aussi que, tu vois, et c'est ça le truc, quoi. Ils ne veulent surtout pas de problème. Après, surtout que je pense qu'un nanosat, tu vas quand même le tirer plus ou moins en continu, non là, je sais qu'il y a des scénarios différents. Mais
non, mais c'est ça le truc. C'est bien ce qu'a dit Naomi, ça va vraiment dépendre de la mission.
Exactement, si tu la tires en continu, tu vois, à la rigueur, un propulseur de Hall, bon, c'est 1 heure par jour, tu fais attention que les communications. Mais là, en continu, tôt ou tard, il faut bien communiquer. Donc, tu es bloqué par.
Oui, mais ce que tu peux te dire aussi, c'est que si tu ne peux pour un géosat, tu vois, pour un gros télécom, si tu ne tires pas pendant 1 heure par jour, si tu tires pendant 1 heure par jour à peu près, donc tu ne peux pas utiliser ton satellite. Enfin, ce qui n'a pas l'air d'être le cas, mais admettons, le coût financier.
Ah oui, bien sûr. Non, il ne faut surtout pas arrêter.
Par jour.
Bien sûr. Bien sûr. C'est évident. Mais là encore, j'ai un petit propulseur. Et sur un petit propulseur, tu peux rien déporter. Parce que là, à la place, tu ne vas pas mettre un truc, tu vois, et tu peux rien faire, quoi. Après, concernant les trucs pulsés, là, les arcs, ils commencent à regarder des choses. Ouais. Donc, je pense que l'idée, c'est peut-être qu'on pourrait faire une sorte de steady state, tu vois, chaque fois. À la rigueur, prendre, tu vois, un arc.
En fait, c'est plus compliqué. Tu fais plusieurs instants.
Voilà. Bon, pourquoi pas? De sorte, tu vois, voilà. Le problème, c'est que les arcs, on a du mal encore plus à les modéliser. Alors, modèle de plume d'arc, bon. Par contre, le modèle d'arc, tu vois, ce qui montre aussi, tu te souviens, ce que montraient nos amis Comat, c'est que quand tu passes magnétique, ça a tendance encore plus à tirer aux forts angles.
Ça part partout. Hein.
Et donc, c'est peut-être encore plus dangereux. Hein. Donc, je ne sais pas. Mais c'est vrai que localement, mais c'est très bref. Mais pendant qu'ils allument le propulseur, tu as vu, il y a 5 kg, je ne sais pas combien, il y a 1 kA là qui passe. En termes de densité, c'est quand même aussi élevé, hein, densité. Donc, rien s'il le faut, ça peut être plus un problème de pulser, peut-être.
les densités sont très élevées. Hein,
Et oui, bien sûr, 10-22, 10-23. Donc, je pense que dans ces placements, peut-être que finalement, c'est plus des problèmes d'arc-sous-vide, ce genre de choses, qui pourraient peut-être pour les communications, peut-être éventuellement poser des problèmes. Que là,
Parce
voilà.
que tu veux dire, les moteurs de haut sont utilisés depuis 20 ans ou 30 ans. Je n'ai jamais entendu dire
Non.
Softhéo aurait peut-être pu commenter là-dessus, mais
Ouais.
qu'ils avaient eu des problèmes.
Non. Après, par contre, bon, moi, je sais que là, nos collègues là, sont plus au courant que moi parce qu'ils ont des interactions avec Airbus directement. Lorsqu'il parlait notamment du signal, tu sais, des fluctuations plasma et du signal, tout ça, le bruit associé à ça, je pense quand même qu'il y a eu quelques soucis.
Ouais.
Et surtout ce qui leur font très peur, je pense qu'ils ont fait qu'on appelle des tests en chambre anéchoïque là. Et en fait, c'est pas du tout conclu. Ils ont des choses, je pense, très variables selon les chambres, selon le pot. Et je pense que ça leur fait peur, c'est ça en fait. En gros, les essais au sol leur font dire, on comprend, c'est quoi ce truc? On voit des choses, on ne sait même pas les analyser. Il y a des fréquences, on ne comprend rien, à quoi ça vient. Et c'est ça qui les met un petit peu aussi, tu vois. Voilà, ils ont peur de manquer quelque chose, quoi. C'est un petit peu ça, je crois aussi, finalement, indépendamment de ce qu'a montré Naomi. Donc, il y a d'autres, tu vois, il y a aussi d'autres aspects, je pense, qui vont être regardés par les collègues. Là, ils sont en train de monter des projets sur tous ces aspects-là, mais je suis moins impliqué.
C'est bien, il y a encore plein de choses à faire sur ça.
Ouais, mais c'est vrai, dans la littérature, même l'UEPC, j'ai rarement vu de présentation sur ces sujets-là, quoi. Ou peut-être que je n'y étais pas.
Oui, c'est ça, où on les a ratés, mais…
Ouais, mais même, ils ont regardé ces vieux trucs. Alors, c'est marrant, tu vois, parce que ce qui est drôle, c'est que, tu sais, on avait fait notre article là, sur la partie, je dirais, propulseur, nouveau concept, etc. Et dans le Review of Scientific Instruments, il y a les Allemands et les Anglais qui ont fait un truc juste sur les moteurs à grille. Un truc, tu sais, de 30 pages qui est plutôt bien fait.
J'ai vu, oui.
Ouais. Et par contre, ils ont évoqué, peut-être même qu'elle a pris des figures de ce papier-là. Ils ont évoqué ces aspects-là, que tu sais que nous, on n'avait pas évoqué dans la partie… et eux, ils l'ont évoqué. Donc, sur des moteurs à grille, ce genre de choses. Quoi. Donc,
on ne l'avait pas évoqué parce qu'on avait rien.
Oui, peut-être rien à dire. Mais eux, c'est vrai qu'ils ont insisté dessus, ils ont mis des résultats. Et notamment, ils voyaient des choses à des fréquences quand ils ont essayé de mettre des antennes de réception. Ils ont trouvé des signaux très, très bizarres. Et donc, ils se posaient plein de questions. Quoi. Voilà. Des fréquences de l'ordre du gigahertz, tu vois. Voilà. Ce cas-là, dans les moteurs à grille, il n'y a pas trop de gyration de la moteur, vous regardez, des électrons. Donc, c'est un petit peu bizarre leur truc. Donc, voilà. Ils s'étaient posé ce genre de questions. Donc, nous, on a aussi une action, on a aussi un postdoc là, avec le CNES qui regarde ces aspects-là. Donc là, plus l'aspect, j'ai mis une antenne pour voir ce que reçoit l'antenne à partir de quand je tire le propulseur. Mais là, pareil, c'est pour la question de l'effet de la chambre, quoi, parce que
là-dessus, sur
les ondes rebondissent
métalliques, je pense que si tu mets ça dans une de nos chambres…
Voilà, donc c'est pour ça que c'est super compliqué. Donc, ils essaient de faire un signal, ils essaient de regarder à différentes positions. Mais ils sont bons, là, les collègues, là, ils sont bons, hein, ils sont capables, ils ont d'idées, ils ont pas mal ils ont d'habitude de ces cavités. Donc, ils regardent un petit peu tout ça. Donc, voilà. Bon, c'est une nouvelle perspective un petit peu pour la communauté aussi.
Non, mais c'est intéressant parce que ça veut dire aussi pour tout ça qu'il faut quand même que le modèle de plume soit fiable.
Aussi, ouais. Tu as vu, on a comparé au tien, finalement, on a comparé à vos mesures. L'avantage qu'il y avait là, si tu veux, c'est que bon, là, les ailes, comme la densité décroît très rapidement, même ils se trompent un peu sur les ailes.
Non, mais tu as 3 ordres de grandeur. Donc…
Voilà, donc finalement, bon, là, c'était moins grave comme au échange de tu vois, c'était quand même un petit peu moins grave. Quoi. Voilà. Donc, le plus important, c'est d'avoir le cœur. Mais c'est pareil, on a pris voilà, un exemple de propulseur, on a pris, c'était très focalisé sur ce qu'on a trouvé. Quoi. Mais c'est sûr qu'en gros, tout ce qui je dirais, si on pouvait en gros réduire la divergence, en gros, toujours du faisceau d'ion, tout simplement, du G, il y aurait plein d'effets. Mais sur les interactions-là, bien sûr, mais également sur l'efficacité, sur tout ça. Donc, en gros, voilà, maintenir le G, tu vois, réduire la divergence, en gros, c'est quand même un élément très important. Quoi.
Depuis le temps qu'on essaye.
Et ouais, et c'est vrai que là, je pense que finalement, et ces aspects-là, moi, je ne l'avais pas en tête, mais finalement, tu vois, ça fait encore plus une remarque pour vraiment un intérêt encore supplémentaire, je dirais. Tu vois. Donc, s'il y avait des choses peut-être sur les nouveaux concepts à proposer, je pense, il faudrait partir sur ces aspects-là, même si, comme tu dis, c'est tellement compliqué. Sur les aspects, tu vois.
On a pas mal regardé, mais on travaille là-dessus avec Alfio, ce sont ces histoires de tuyères.
Oui.
Pour les VAT, c'est sans doute eux sur lesquels tu verras le plus d'effets parce que ça part partout.
Ouais.
Sur les autres, on va dire, je sais pas, les ECR ou les RF, tu ne gagnes pas grand-chose avec ta tuyère en termes de…
Oui, non.
C'est quand même déjà des trucs qui partent.
Bien sûr, bien sûr.
Je sais pas.
C'est vrai que peut-être parce que pour les petits, encore une fois, il y a des contraintes, on ne peut pas déporter les choses, on peut pas. Comme tout est miniaturisé, là, tu vois, le moindre que peut-être ça va être un peu plus important de gagner.
Peut-être que finalement, le peu que tu gagnes
est efficace, parce que finalement, tu ne peux rien faire d'autre. Là, tu ne peux pas le déporter à 1 mètre, le truc qui non, c'est pas possible. Donc, si tu veux, là, tu n'as pas trop de choix.
Très intéressante discussion.
Mais tout le monde peut aller en français, c'est dommage. Mais on laisse ouvert, donc voilà.
Ouais, non, on discutait.
Non, mais
Non,
c'est vraiment intéressant cet aspect pour les tout petits satellites.
Non, non, mais c'est ça. Et qu'on n'avait pas du tout au début. Je ne pensais pas. Ouais, comme j'ai pas eu de retour de trucs, de problème. Mais les petits, c'est vrai qu'il y a aussi peu d'expérience. Enfin, l'expérience comme moi j'ai.
Ça commence.
Voilà, après ça commence. Voilà, exactement. Mais c'est vrai qu'il n'y a pas eu non plus trop de retours et peut-être pas vraiment de problème. Mais on ne savait pas, quoi. En fait, c'est intéressant.
Et tu vois, le speech qui vient de Ashley va être intéressant de HP.
Oui.
Parce que c'est vraiment sur cette interaction-là.
On va regarder ça.
Plus Spacecraft en général, mais.
Ouais, je vais regarder un petit peu. Mais alors, par contre, je ne comprends pas parce qu'au HB, il y a aussi le collègue tunisien là, qui est à Brême.
Oui.
Là. Il fait aussi le modèle de plume parce qu'il m'a contacté. Et je vais voir la différence. C'est le même ou je ne sais pas. Parce qu'il était au HB aussi.
Je ne sais pas, tu peux leur. Oui, mais
non, mais
c'est la même
pas.
boîte. Mais là, c'est OHB. C'est OHB Suède,
alors que lui, c'est OHB Brême. Mais c'est OHB.
OHB, quoi. OHB Allemagne.
Ouais, écoute, je vais regarder un petit peu ce qu'elle fait. D'accord, ok. Donc, je vais être. Bon, je fais une petite pause, moi, d'accord?
Oui, moi aussi.
Ouais,
je vais prendre un petit café. Donc, tu prends
et tu le fais cet après-midi, ok? Ouais, non, c'est Alberto cet après-midi qui va le faire.
De toute façon, cet après-midi, il y a 2. Alberto, il fait déjà la table ronde.
Ouais, tu fais celle avant alors, si tu veux.
Je peux faire n'importe, je suis là à 14h.
D'accord. Christophe?
Pas de problème.
Ouais, est-ce que vous m'entendez?
Maintenant, oui.
Oui.
Bon, je vous laisse,
Ouais,
à tout à l'heure.
Désolé
un
pour le
problème avec
problème
le
de
micro?
son, mais comme on est obligé d'accéder, ouais, ça marche pas avec le micro via le navigateur. Enfin bon, bref.
Ah merde.
Du coup, par le téléphone, ça marche.
D'accord.
Bon, c'était une discussion intéressante. Bon, on les avait vus, donc on sait un peu ce qu'ils font, quoi.
Non, mais c'est ça.
Après,
pour les satellitiers, c'est super important. Pour prendre quelqu'un comme moi, c'est très. Je suis très amoureux. Mais je ne doute pas que ce soit très important.
Après, effectivement, aujourd'hui, on a plus de problèmes. Bon, c'est ce qui a été mentionné par une des personnes avec le bruit du moteur lui-même.
D'accord.
Le bruit électromagnétique.
Ouais, ça aussi, ça va être une thématique importante. C'est des choses
là, on a des problèmes de
quoi.
couplage, on va dire, entre les récepteurs et le moteur qui se comporte comme un émetteur, quoi.
Bien sûr, c'est un émetteur. Oui. Il faut qu'on avance là-dessus aussi sur les caractérisations, mais c'est pas facile. On n'a pas de on n'a rien. On n'a pas de chambre.
Ah bah effectivement, il faut des chambres spéciales, mais nous, on fait ici sur les moteurs qu'on utilise, on fait des tests de mesure de bruit électromagnétique, mais il n'y a pas beaucoup de chambres, hein. Il y a aérospatiaux.
Non, il y a aérospatiaux et puis les Américains
Les Américains, voilà. Exactement.
Mais après, c'est compliqué, et la question qu'on se posait là avec Laurent, c'est est-ce que vous voyez la même chose sur 2 chambres différentes?
Je ne sais pas, je ne suis pas sûr qu'on ait fait des tests sur 2 chambres différentes.
Non, ça doit coûter cher, mais il faut être sûr de la chambre aussi. Et, donc, bon, il faut qu'on réfléchisse à ça en France. Bon, l'ESA, hier, dans ce que disait Davina, c'est que l'ESTEC va construire aussi une chambre anéchoïde. A priori, ils partent là-dessus, mais je pense qu'en France, il faudrait qu'on ait.
Non, ça, c'est une vraie question.
On commence à y réfléchir, nous. C'est compliqué. Hein. Tu as vu à Aérospatiaux aux États-Unis, c'est compliqué de tirer.
Oui, j'y suis allé. C'est quand même un gros moyen. Et puis.
C'est compliqué. Ouais.
Après, peut-être sur des petits moteurs, c'est possible de faire une chambre qui soit complètement transparente, parce que chez Aérospatiaux, c'est une espèce de verrue greffée sur la.
Oui, tout à fait. Et Aerospace Corp aussi, en fait, tu as la chambre anéchoïde. Je suis allé la voir, et après, tu tires dans ton plasma, part dans la chambre. Donc, tu as aussi une grosse région qui n'est pas fermée.
Oui. Bon, c'est une question, effectivement, et là, on aborde le problème via les microsatellites, mais même sur la tendance quand même sur les satellites, en tout cas, il y a une tendance qui est de faire les satellites plus petits, même pour du business, avec plus de bras qui se déploient, etc., un peu dans tous les sens, parce que bon, quand on est petit, il faut arriver à tout mettre, donc ça veut dire déployer les thrusters, déployer des radiateurs déployables, déployer les antennes, etc. Du coup, on a quand même des problèmes d'arriver à accommoder tout ça. Hein.
Il y a peut-être un peu de coût après aussi. C'est bien beau de mettre des trucs qui se déploient, mais.
Mais enfin bon. La tendance quand même est en général de faire des satellites plus petits.
Ça, c'est une question qu'on va, je pense, aborder dans la table ronde ce soir. Moi, c'est vraiment une question. C'est quoi est-ce qu'il y a une taille optimum? On se pose la question. Parce qu'on voit que les petits ont tendance à grossir quand même et que les gros ont tendance à se réduire. Ça va converger ou pas?
Je ne sais pas.
C'est intéressant ça. Okay.
Mais c'est vrai que quand même, nous, on voit que la tendance, c'est plutôt de faire des satellites plus petits.
Ouais, mais il doit bien. Enfin, l'optimum dépend aussi de l'objectif, probablement.
Bien sûr. Tu ne vas pas faire une mission télécom avec
Avec
un nanosat quoi, en orbite géostationnaire. Tu as quand même besoin d'un minimum.
On
de
est d'accord,
puissance, mais quand même, on cherche à faire. Le but étant aussi de réduire les coûts au lancement. Si tu peux en mettre deux dedans.
Évidemment.
Donc, c'est vrai que les contraintes, on va dire, d'accommodation de tout ce bazar entre la propulsion et tout ce qu'il y a, donc tout ce qui est senseur, MPCS et payload, commence à devenir complexe.
C'est bien, ça vous fait du travail. C'est génial le travail.
Ouais.
Je vous laisse 5 minutes, je vais prendre un café avant qu'on redémarre. Laurent n'a pas le droit.
Ok.
C'est cool. À tout de suite.
À tout de suite.
Je vais couper le micro.
Non, mais on peut.
Bon.
Ça va?
Bon, on en avait déjà parlé, donc je ne découvrais pas le truc. Mais...
Oui, bien sûr. Mais c'est ça l'avantage. Oui,
Après, il y a sur cet aspect aussi, sachant que le plasma, lui, il évolue dans le temps, il n'est pas constant.
Ouais.
Il me semble qu'il y avait une publi à un moment, mais qui est assez ancienne, où il montrait qu'il y avait des espèces de modulation, on va dire, autour de la fréquence liée au bruit du plasma, quoi.
Non, c'est sûr. Là, en fait, on a là, des modèles de plume, on prend des résultats qui sont moyennés dans le temps, et voilà, on va passer à cet aspect-là. Après, la modulation, enfin, quand un moteur marche bien, il est censé quand même être modulé par rapport à un point nominal autour de 20-30%, même pas 20% en plus, voilà, plus ou moins 20%.
Ouais.
Quoi. Voilà. C'est pas un propulseur à arc où là, tu tires, tu vois, là, d'un coup, plaf, tu as un arc, tu tires à 1 kA. Là, par contre, Et en plus, souvent, dans un propulseur d'arc, si tu as tendance à avoir une divergence qui est plus. Sauf si tu luttes, tu as tendance à avoir une divergence qui est beaucoup plus importante. Et donc là, à part si tu mets un champ magnétique, etc., pour essayer un peu de focaliser, mais ça part partout. Hein. Donc là, c'est
moi, les trucs métalliques, genre Comat, c'est un truc qui m'inquiète quand même. Hein.
Mais je sais bien. Moi, je me doute bien.
Tu vas balancer du métal partout. Après, ça risque d'être une grosse source de bruit quand même.
Et là, c'est métallique en plus.
D'un point de vue électromagnétique. Et puis, tu auras la densité d'électrons qui va augmenter là, de temps en temps. Du coup,
Ah ouais, là, les densités de plasma, dans l'arc, après, une expansion, mais quand même, c'est 10-22, 10-23. Hein. C'est pas 5 ordres de grandeur, tu prends. 5 ordres de grandeur, là, le nu sur oméga, nu va tendre vers oméga. Hein. Donc là, l'absorption.
Je pense que là, on va avoir. Enfin, moi, je pense qu'on aura beaucoup de problèmes de compatibilité. Peut-être pour un nanosat qui fait des trucs, ça peut marcher. Après, pour un satellite
plus gros, ouais. C'est vrai,
parce que
sur
lequel tu as des contraintes multiples, je suis hyper réservé, quoi.
Ouais, je comprends. Non, mais je comprends, c'est vrai.
Je pense que c'est pas demain, quoi.
Non, c'est vrai, quoi. Ouais.
Déjà, rien qu'un métal, c'est quand même fondamentalement assez sale, quoi.
Ouais. Quant à ceux qui font des tests avec l'iode, l'iode, en plus, c'est hyper corrosif. Je ne sais pas comment ils font, en fait, Ils doivent vraiment bien maîtriser leur procédé, leur truc, parce que je sais que moi, les premiers qui avaient travaillé dans l'iode, ces gaz-là, c'était impossible, quoi. C'est-à-dire qu'en réalité, ils bousillaient les instruments, ils bousillaient tout, quoi. Donc, la chambre, n'en parlons pas. C'est pour ça que certains avaient arrêté, je pense. C'était même pas caractérisé. Je pense que c'est les premiers qui avaient travaillé dans l'iode, ils se sont confrontés à des problèmes
à un moment, il y avait un programme américain, je ne me souviens plus comment il s'appelle.
Le bismuth. C'est pas le bismuth?
Non, mais ils ont lancé un petit satellite fonctionnant à l'iode, là.
D'accord.
Je ne me souviens plus comment il y avait eu des présentations. Bon, je ne sais plus, là.
D'accord.
Lors d'une conf à Rome ou un truc comme ça.
Ah, d'accord.
Mais bon, ils continuent à bosser quand même sur l'iode, etc.
Moi, je suis ça d'un peu plus loin, mais
Après, l'iode m'inquiète. Enfin, ça m'inquiète un peu moins que un moteur fonctionnant au métal.
D'accord, ok.
Parce que du métal, tu vas en balancer effectivement un peu partout. Enfin, des ions, peu importe le métal. Et alors là, dès que ça va arriver sur des surfaces, ça va se déposer, tu vas tout métalliser.
Oui, bien sûr.
Non,
je comprends.
Et là,
je peux. Et puis même nous, après, quand on voit, moi, quand je vois des propulseurs archoïdes, qu'on commence à regarder, moi, je fais des petits modèles, etc. de ça. Quand tu vois des ions multichargés, même pour nous, en termes de modélisation, de physique, on a du mal. On n'a même pas les données, on n'a rien, quoi. Titane 7+, qu'est-ce que tu veux que j'ai donné sur le titane 7+?
Oui.
Je suis obligé de faire des hypothèses un peu grossières, voire même Mais alors même le titane, hein, de la littérature, l'aluminium, on trouve des trucs, mais le titane, j'ai trouvé aucune donnée, quoi.
Ouais.
Ça n'existe même pas. Il y a des articles qui disent que ça n'existe pas. Donc c'est très dur. Donc on est obligé. Ah ouais, pour que ce soit marqué noir sur blanc. Il y a quelques années, donc je me suis tapé plus de 1500 références. Là, je me suis rien. Je trouverai le cuivre, oui, ça y est, le cuivre commence à être pas mal documenté, mais c'est moins intéressant pour la partie arc sous vide. Ils avaient vraiment de meilleures performances avec du titane, mais c'est le moins documenté, quoi. Et dans la colonne, on dit des fois bon, de prendre des éléments périodiques un peu proches, mais c'est des matériaux, c'est des éléments moins connus, quoi. Donc, zirconium, truc, bon. Donc, non, mais c'est vrai que même pour les données, c'est vraiment, on arrive vraiment. Donc, ça que mettre des chiffres, il va vraiment falloir aussi des mesures, quoi, des estimations. Enfin, on peut ne pouvoir faire que des estimations, je dirais, un peu grossières, quoi. Parce que honnêtement, autant sur du Xenon, on commence à être, voilà, on a des données, ça on connaît bien, on peut se tromper, mais quand même. Mais là, par contre, on doit même construire des outils, c'est super compliqué. Et tu passes ton temps à chercher les données, en fait. C'est super compliqué. Et même les gens de la communauté qui connaissent très bien le suivi m'ont dit que ça n'existe pas. Donc, ils ne connaissaient pas, ils connaissent très bien la littérature. Ils me disaient, même de simples collisions, électrons. Alors là, on trouve quelques éléments, un petit peu sur des bases données américaines, mais souvent à des énergies très fortes, électroniques, qui quand même nous concernent un peu moins. Plutôt du KEF, tu vois, quand même, on n'en est pas là. Donc, ouais, c'est un peu. C'est compliqué de tous les points. Alors, quelle heure il est 11h, on va commencer. Okay, so I think that we can start the session. And the first talk will be given by Ashley Alok from OHB so in Sweden, and she will talk about the modeling plume spacecraft and direction for InnoSat. Please, Ashley. You have 15 minutes and 5 minutes of question, and you can share your screen. Yes.
Do you see my screen?
Yes.
Great. Thank you for the introduction. My name is Ashley. I work at OHB Sweden, and today I'm here to talk about modeling plume spacecraft interaction for our satellite platform called InnoSat. There's lots of different OHBs. We are the one in blue there. So we're in the space systems group, I would say. There's many different subsidiaries and quite a lot of employees. I guess the most famous one that everyone's heard of is OHB System. We get confused for them a lot, but we have a great working relationship with them and several of the other subsidiaries. So it's a very nice group with a quite wide group of competence. So it's a very nice working environment. We were Swedish Space Corporation for many years in just outside of Stockholm, and in 2011 we were purchased by the OHB Group, and it was funny. That's when I was starting to talk to them about a job, and they gave me a business card that said Swedish Space Corps, and when I called the number, it said "Thank you for calling OHB Sweden." So right at the turnover there, and they have grown quite a lot since then. I think we did the introduction. I met everybody at the company within 10 minutes when I first joined, and now we have over 90 people. And I don't even think I've met all of them, but that could also be because of COVID. We're a little bit farther out from Stockholm now, largest system integrator in Sweden. And some financial numbers. I don't work in the business department. We make some money. Yeah. Our areas are small satellites. That's what I'm going to talk about today, mostly. We also do propulsion for larger satellites. That's where I work. We also have AOCS department upstairs, and all three kind of converge in AIT operations. And these guys work very hard, that group. So our history, you see at the top, the black and white photos, those are satellites that have come and gone. Nice Nordic names. So this is Swedish Space Corporation times. One of them is not black and white. That's not a mistake. Odin is still going 20 years later. Very over-designed satellite, that one. And then all of the color photographs are current missions. You can see the changeover right about here. Smart 1 and Prisma started to be more international, less Nordic named missions. And then we have all of our subsystems that we've been working on over the years. AOCS as well for some of those. And then over here, you have starting with our InnoSat platform, GMST was the first one. And we'll have MATS going up shortly here, our Arctic Weather Satellite, ICE, and SWS coming up. So for small satellites, this picture is, I mean, if you have a picture of a rocket, why not show it? This is GMST going up in January of this year on Rocket Lab's rocket in New Zealand. A successful launch, and a successful mission for GMST. Details about InnoSat. It was developed in collaboration with Swedish National Space Agency, which we used to work closely with when the company was Swedish Space Corporation. It's developed as a platform to serve a variety of Swedish scientific instruments, as well as a variety of commercial missions. Here you see some pictures of the platform development during qualification. Just like I think the first speakers this morning were saying, one size does not fit all. So we have three, and within those three, they can, there's quite a lot of margin as well, small, medium, and large. So it's a family of small sat platforms. And we go from 30 to 200 kilograms. It's built around a set of reusable core architectural hardware and software elements. Specific extensions and adaptations can be made on a case-by-case basis. So you have small. So the payloads here are 15 kilos and up to 25 kilos for medium, and large up to 60 kilos. The power level is around below 40 watts for small, and medium sits around 40 watts, and large can go up into the 100 watts and more, depending on the application. 28 volts unregulated as power supply. We aim for about 5 years. What else could be? And I think they've all had propulsion on them. It doesn't have to, but we have that option, which is the subject of the talk here. An example of small was GMST was a small version, and then MATS will be a medium, and both AWS and ICE will be a large version of the satellite platform. It's compatible with a range of launchers. This is the one on the left that we have used. And just the mission overviews, MATS was for SNSA, a scientific mission. Optical payload, mass was 60 kilos, and it should launch coming up soon here. GMST launched in the beginning of the year. Total mass of 50 kilos, little platform, small, with RF payload. Arctic Weather Satellite is for ESA, meteorological. It'll be large with microwave payload, and it'll be 120 kilos, and that'll be launching 2 or 3 years from now. And ICE is also for ESA, IOD mission, large hyperspectral payload, 100 kilos, and launching about the same time as Arctic Weather Satellite. And here you have some pictures of them on the bottom. And the two on the right are just obviously artist concepts still at this point. This is GMST, it's a picture of it in our facilities in Kista. This is already went through all of this information. This was our flight mission to give it flight qualification, our platform. MATS, another close-up picture of MATS, which should launch very soon. Arctic Weather Satellite improves global weather monitoring through a constellation of polar orbiting small satellites. We really enjoy having the Earth observation and the environmental considerations for the missions. It's really rewarding to be working on these projects. Also in the subsystems that we do for these projects that are interested in addressing global warming. So InnoSat, flexible design for a wide range of missions. I guess you could say it's off the shelf-ish. You have just enough choices to where we can meet a wide range of missions, wide range of payload mass, mission total impulse, delta V maneuvers, but not too many choices so that it starts to have a large non-recurring cost. So it's kind of a compromise in there. So we still have off-the-shelf costs and schedules, but we can still accommodate and adjust to a reasonable degree. So no single propulsion unit covers all of the UNISAT needs. So we pick the propulsion unit on a mission by mission basis. It's selected based on mission requirements. So we do not have a baseline propulsion unit that we have 50 on the shelf and that's what we use. But this creates a need for a fast, cheap, and reliable tool for plume spacecraft interaction. So modeling the plume spacecraft interaction. We use something called OpenPlume EP. You may have heard of it. It's developed in-house by OHB System, our sister company. It uses 2D ray tracing approach. The thruster parameters are extrapolated downstream using the 1/r² approximation. It's an engineering tool to quickly calculate the impact of thruster or equipment placement. It can model a variety of EP propellants, including xenon, krypton, argon, magnesium, indium. I've even done brass for these ablative anodes. So it's very adaptable. The other thing I should mention is it's free. The cost of this program is that they want to have your email address so that they know who is using their software. So it's a very reasonable price tag. So when you're using the program, what does it want to know? You have a few different ways of inputting the information, but we use the experimental interface. So this is a measured current density distribution, ion density distribution, and thruster contamination is something that they recently implemented on our request. And this is the droplets coming out. So it's not contributing to thrust necessarily, but it is something very important for us. And when you see people giving talks, presentations, this is the part of these curves that's interesting for the thruster suppliers, and understand that. That's where they're getting their nice efficiency numbers from. Sarah was saying this morning, nobody talks about efficiency, and yeah, all thrusters have a tough time competing with electrospray efficiency. But I have to say, electrosprays don't talk about the droplet emission either from their thrusters, and that's really important for us to know how much of these often solid and condensing propellant, how much of that is coming out of the thruster and at what angles. So these far field plume it's very interesting for us, as well as the uncharged droplet distribution coming out of the thruster. I realize that everything is in a very fast pace these days, and this stuff doesn't usually make the test plan, but it would be very helpful for us if we could have more information on these parts from the thruster suppliers. So what is the OpenPlume calculating? Ion energy, current density, forces and torques, erosion, deposition. And deposition is both the deposition from sputtered products as well as the primary deposition, which you don't get for things like xenon and krypton, but you do get from things like indium, and if you have an ablative, or if you're ablating metal from your thruster as your propulsion, those sorts of things. But so how do we use the tool? So let's say we have, this is not really real. This is kind of a made up satellite. It goes very fast to draw it. And then just in the beginning, if we're looking to accommodate payload as well as a thruster, what we can do is just throw some boxes in. It goes very quick to calculate. And you have kind of an equipment stay-in zone. And you have a thruster, it's usually on its own box, and then you model the thruster as a point source. And you can very quickly, not so refined mesh, just get an answer of, okay, the plume is going to hit here and here, but nothing else. The solar array is fine in this example. And we're just assuming that the thruster supplier has ensured that the box can withstand its own plume. So we tend to ignore that one and look over here. And it's a really nice tool because you can quickly see, okay, oh, it did catch the edge there of that box. So we need, what happens if we just push that out a little bit, or push these in a little bit on the matter of centimeters. We know that these surfaces are fine. So if we can just shift the thruster out just by 2 centimeters, everything goes away. And you actually don't even have to do, if you're really in the beginning stages of a project and you're just trying to mapping things out quickly, you don't even have to run the calculation, because you can see it runs the erosion module first before it does contamination. And you can see in the time that it's taking to run the erosion module if you've cleared all surfaces or not, because it's only going to calculate if there is an interaction. So you could
2 minutes, please, Ashley.
Oh, thanks. You can very quickly see whether you have a good thruster placement or not, and move things around. Let's see. Yeah, and then and this, just by moving the thruster out 2 centimeters, we managed to isolate the impact of the plume to the thruster box itself, which we assume the thruster supplier has made to withstand the impact. But sometimes there is someone who says, the spacecraft comes back, we have to have this thing here and we can't move it anywhere. And then of course we can calculate the relevant parameters on that surface with a fine mesh. And it's very easy to use, very intuitive, and I can calculate all the things I said. Most importantly, really, for these small satellites is considering the alternative propellants, which are almost not even alternative anymore these days, but the solid and liquid propellants, the non-gaseous ones. Deposition and redeposition become really important, especially for optical equipment. So it is really important to get this information from thruster suppliers so that we can properly model the interaction on our equipments when we can avoid them. And it becomes very difficult to avoid them, especially with the larger small satellites. So in conclusion, InnoSat offers a flexible off-the-shelf platform. It's developed in 3 size classes to meet a wide range of missions and payloads, compatible with multiple launchers, flight proven. Payload and thruster accommodation is modeled right now with OpenPlume EP, engineering tool to calculate erosion, deposition, redeposition. Redeposition is, of course, what's the classical one from Hall thrusters and ion thrusters. Deposition is kind of a new one that's becoming very important. Current density, ion energy, fast simulation time. So we rapidly converge on a preferred hardware arrangement. More refined mesh can be used when you can't avoid equipment plume interaction. Can model a wide variety, almost any propellant, including indium and iodine. However, the intuitive results, they are only as accurate as the thruster plume model that we receive. So this is a very important input, as I said. I think I'm about right on time there.
Yeah.
Thank you very much.
Thank you, Ashley. Thank you for an interesting talk. So now we have time for a few questions. Please, in the audience, any question, any comment? Yes, Stefan.
Hi, Ashley. Nice to see you. Great talk. I've got a question about the last remark in your conclusion. I mean, you said that you need accurate data, accurate plume data, right? Of course, which I understand. Which type of data do you need then? Or...
We would like to have current density, ion energy, and especially in the case, not particularly with the Hall thruster, but with, for example, FEEP electrospray thrusters, we need to know droplets being emitted, preferably per angle per time, because there is non-ionized neutral droplets coming out of the emitters. And that's probably at this power level, you're not getting a lot of erosion. You're not getting so much parasitic torque, but you are, I mean, you're covering up star trackers and stuff like that. So that's the main thing. And sometimes it's not even measured. It's not even considered. They just want to measure the performance and cite the numbers and the great efficiency and move on.
And the charge state, I mean, the multiply charge ion fraction is also of relevance for you?
I'm not sure if that one is particularly modeled in this. I have to remember if you can do doubly. What we usually do is the singly charged, because I mean, what goes straight out is not really interesting. I mean, that we can just look at the performance and then we can do the mission analysis. But it's what's at the far field that's interesting for us. And I think that if you can get the singly charged ions there. And we have a factor of safety, and then we can show that parasitic torques and erosion are well under what would be what our limits are, then that's fine. We don't really care beyond that. It's more the droplets, I think, that are creating a new problem.
Okay, thanks.
Yes, we have one question from Christophe.
Yes, can you hear
Yes.
me?
Yeah.
Yep.
No, it's just to answer to this topic. I think it depends on the thruster, but if it's all effects thruster, we are for sure interested by multiply charged ions because they do not have the same energy, so not the same impact on the satellites. So yes,
For like a large,
fraction of
for a large satellite that has a solar panel that's turning into the plume, absolutely.
yeah, yeah.
Thank you for the comment, Christophe Theroux. Christophe Koppel wants to ask a question also. I will.
Salut, Christophe.
Bonjour, Ashley.
Bonjour.
Just a question. Thank you for your presentation. How did you validate this tool? And did you compare with other tool, and which tool did you use it for comparison?
I was thinking I might get a question from you. And my answer is simple. I did not, it's not my tool. I did not validate it. OHB system validated it and has shared the material with us, but it is confidential, so I can't present it. They have validated it. They have compared it with other tools. And we were satisfied with the information, but it's unfortunately not academia where we're working now. So, but I'm sure they will make the information available to you upon request. They're very, very nice guys.
Thank you.
Okay.
Thank you. So is that okay? So I think we have to switch now to the next speaker. We thank again Ashley for this interesting talk, and now we switch to the talk of Tatiana Pirotti from Madrid in Spain, and she will talk about development of a low power cylindrical all thruster. So please, Tatiana, it's up to you.
Thank you for the introduction. Let me know if you can see when I share my screen, please.
Yes, we see it.
Great, thank you. So I am a PhD student in the University Carlos III in Madrid. I'm going to talk about the development of our low power Hall thruster, which is a cylindrical one. So I will go through the motivation of the design of this prototype and the introduction of the prototype itself. Then we'll talk about the experimental investigations that we could perform so far with the different kinds of neutralizer for the thruster and the very first results that we obtained. And then I would talk quickly about some simulation results that we got about the discharge of this thruster. And I will mention the first conclusions that we got on how to improve the design and the future investigations that we're planning. So first of all, the motivation, well, we wanted to have a low power thruster operating between 100 and 300 watts. And we picked the Hall thruster for the maturity of the technology and the heritage that exists. But we thought that due to the issues that arise when downsizing Hall thrusters, the CHT geometry, so the cylindrical channel, was interesting since it kind of avoids some issues related to power losses with the volume to surface ratio. It reduces pole erosion because we completely remove the inner pole, and it makes it easier to handle the thermal management and also to manufacture the parts because we have less smaller parts inside of the channel. And same, we have also more available space to generate the stronger field that is needed for electron confinement at this power level. Also, it's quite interesting because this type of geometry already exists and there's work that has been done in the last 2 decades, but there are not so many existing in the world and none of them is flying. So there's obviously still some work to do about it. So we want to learn the specificities of the cylindrical Hall thruster and how to optimize the design. Of course, one issue that remains is having a self-heated and robust low current hollow cathode that is not solved by the cylindrical geometry. So here you can see on the right a schematic of our prototype. As you can see, the channel is fully cylindrical, which makes it simpler than some designs that have a partly annular channel. The inner dimensions are simply inspired by the thruster of Princeton that operates around 100 watts. And the magnetic field in our case is generated by two coils that you can see here in orange that are operating in a direct configuration. And they allow us to modulate the field depending on what we want to test. And in gray, you can see the rest of the magnetic circuit, which is made of soft iron. And you can see the color map that displays the magnetic field with large gradients and very large magnetic flux on the axis and at the bottom of the channel. In orange as well, you can see the copper anode that is placed in the most shielded location inside of the chamber to reduce electron transport. And the injection is done through this anode to enhance ionization. And we selected the materials in order to create a sort of heat conduction path that protects the coils from overheating. So for the experimental investigation, the first thing is that we needed the cathode to operate this thruster. And for simplicity, we first tried to operate it with the thruster that was available in our lab, which is a 5 amp hollow cathode that you can see on the right, on the top picture. The problem is that we already knew that it would be oversized for this 200 watt approximately cylindrical Hall thruster. So in fact, the current provided by the cathode and the mass flow rate of the cathode are 5 to 10 times greater than the properties of the thruster itself, which is quite inappropriate for the operation. And in addition to this, the cathode itself alone in the diode mode with a planar anode, it shows quite poor operation. So it operates in crew mode with lots of oscillations, and it requires a high total current and high mass flow rate to sustain the discharge. However, we managed to ignite both the anode and the cathode on both operating on krypton and both operating on xenon, as you can see on the two bottom pictures. In all cases, we needed to keep the keeper on of the cathode, and most of the operating points that we tested were in the current saturation for the anode. So we had quite low discharge voltage, and a large discharge current, which is quite the opposite of what we expect as an operating point for a Hall thruster, since it means that we have poor ion acceleration and some heating of the thruster itself and large losses to the walls. So then we thought if we are having troubles operating the thruster with the cathode because the cathode is oversized and the mass rate of the cathode itself is too high compared to the anode, then let's just completely remove this extra mass flow rate and use the hot filament as a neutralizer. So that's what we did. And this also allows to have better direct control of the emitted current. So to understand how to use a hot filament as a cathode, we did some preliminary work to size the filament. So we computed first in a vacuum the special limited current and the thermodynamic current, which you can see on the top right figure here. And then we also measured this current again in a vacuum with the filament and two different kinds of anode. And we observed that the current that we could get was potentially enough to operate the thruster. However, there was a big mismatch between the computation and the measured values, which is certainly explained by the many different experimental errors. But we went on, and we tried to compute the same thing, the current that we could get from the filament in a plasma. So we made a simplified model that accounts for the particles collections and emissions, and computes the voltage drop along the filament and the current that we get. And from this, the results that you can see on the top right figure, we estimated that we would need 2 filaments to reach a reasonable target discharge current for the thruster operation. So we tried it and using 2 filaments, and we managed to ignite. And the few observations that we got from this was that we needed a large heating current in the filaments to allow for ignition. That if the heating current was too small and the mass flow rate of the anode and the voltage bias of the anode were too big, we had mostly arcs, but not a proper discharge stable. But eventually we managed to obtain that DC discharge, and it was also in voltage control when the mass flow rate was below a certain threshold, which is 4 SCM in this case. And we observed that after ignition, since the heating current of the filament and the discharge current both flow inside of the filaments, they contribute to heating up the filament, and there is a drift of the total current and the heating. So this is still something that we need to understand to test and find the values that work to stabilize the discharge. Unfortunately, we couldn't go on for the moment because the filament failed. But this is so far promising. And on the bottom left picture, you can see that the filament apparently deposited some conducting material on the channel of the thruster, which could eventually become an issue for the operation. So here, this is the very preliminary results that we got measuring the plume with the Faraday cup, doing an angular sweep in the plume. So on the left side, both of them are done with the filaments operation. On the left side, you can see that this curve was obtained when the thruster was switching continuously between voltage control and current control, because we were exactly at the threshold flow of the anode. And what you see is actually time oscillations of the plume. So it's not exactly optimal. We still need to find how to stabilize the discharge to bear it well, but at least we obtained the voltage saturated discharge. And overall, the performances are not yet very good. So this also will require some improvement. And on the right, you can see the much more stable and steady currents of the plume in current saturated discharge. However, you can notice that there is a small asymmetry that is probably due to the filament itself, due to the bias, the potential of the filament inside the plume, and some asymmetry of the field. Then I wanted to talk quickly about simulations, because in parallel to the experiments, we wanted to try to model the thruster operation. So we used Hyphen, which is a hybrid multi-thruster code that existed, that is already being developed by EP2. And it models the heavy species as a particle in cell and the electrons as a fluid in 2 different meshes with 2 different timescales, and including some free parameters for the turbulent effect. And we managed to adapt this existing code to the cylindrical Hall thruster geometry with the properties that you can see on the bottom left here. But so far, the turbulent parameters are still arbitrary. So the results are not quantitatively representative of the reality, but they give ideas of the trend of the behavior of the plume, of the total discharge actually. And the idea is that after, when we have experimental results of the thruster, we can tune these free parameters in order to match to fit the simulations to the experiments. But we observed some things about the cylindrical Hall thruster operation. For instance, we saw that the ionization happens near the anode and injector, which need to be together, which needs to be done in the same region. And this is the specificity of the cylindrical geometry. And we also saw that the ionization and the acceleration regions are quite different from the annular Hall thruster, the traditional one. And this is due to the radial effects related to the geometry of the magnetic field. These are some more conclusions that we got from the simulations. So on the left, you can see plots of the electric field in the plume of the thruster, depending on two different cathode positions. So even if the locations are not necessarily realistic, it gives an idea of how the electric field is affected. And so we see that the cathode position affects the beam angle and also the downstream ion production. Then in the middle, you can see the ion production. So what we observe is that if we change the channel length of the thruster, this will have an effect on the beam angle and mostly on the wall losses, because we have some ion recombination and reionization here at the side wall near the exit because of ion impingement. And on the right, you can see a plot of the plasma potential with different anode positions, which is also the injector position in this case. And what we observe is that we always need to keep together the anode and the injector to enhance ionization, and also that the location of these two really affect the beam divergence, the current efficiency because of the electron shielding, and the ionization. So we already have some idea of how to improve the design from these experimental and numerical results.
Tatiana, 2 minutes, please.
Thank you. So first of all, we want to avoid during the experiments this current saturated discharge. So for this, we thought that we could probably try to increase further the magnetic field, or even combine permanent magnets with the electromagnets that we already have. We could potentially reduce the anode area. We already know that we need to decrease the mass flow rate in general, both mass flow rates, I mean. And we definitely need to find a cathode that operates at low current. And then understanding transport mechanisms will certainly help us to operate better. And then we want to also improve the partial efficiencies of the thruster, limit the power losses, and so the consequent heating of the thruster. For this, we're going to try to reduce the channel length, as I showed before. We could try for the filament case to shield it to avoid too much radiation towards the channel, and optimize the neutralizer location and anode location, as I said before. For the future, we obviously need to complete the full characterization of the operation of the thruster with the direct thrust measurement and diagnostics of the whole plasma plume. And this at different operating points with an adapted cathode and or with the filament neutralizer that now that we know a bit better how to operate it at a good point. And we have some ideas of how to counter the issues that we had that led to the failure of the filament. And eventually, when we have all these results from the experiments, we want to fit the simulations to the experimental data. So to conclude, we managed to design and build this prototype of cylindrical Hall thruster. We managed to use computations to size the hot filament and use it as a neutralizer. And we successfully ignited the thruster with both the hollow cathode and the filaments. We started performing some measurements of the beam properties, but we still need to do a lot of them. And we managed to model the discharge of this thruster. We already have an idea of how to improve the design and also how to improve the operation. What remains is to fully characterize the plasma, as I said before. fit the experiments to the simulations and solve the neutralizer issues that are so far being very problematic. And then eventually the idea is to do a second iteration of the design to have a better prototype.
Okay.
Thank you very much.
Thank you, Tatiana, for your interesting talk on cylindrical hole thruster. So now the paper is open for discussion and question, please, in the audience. I see Stefan with the end, but no. Question, maybe I can start to ask some question. I have a question about the filament.
Mm-hmm.
The filament, do you have any problem with, I mean, lifetime during your test?
Yes. So let me go back.
Yeah.
Okay, it's not really working. So as you can see in this picture, in the bottom left picture, we have a lot of sort of evaporation of the filament material. And the problem in this case, so on the bottom right picture, maybe you can see that what we did is that we put two filaments that are coiled on the top and on the bottom of the channel and very close to the channel edge. And the issue that we had is that the whole system was fixed. And since the temperature that we reach is, as displayed on the top graph, is very high. And so we had thermal expansion of the coiled filament. And so it did a sort of belly and moved into the plume. And so it was directly exposed to the plasma species. And I think that's the reason why it failed, because it broke really exactly where it was exposed to the plume the most. So I think that's the biggest, I mean, evaporation due to the heat and then exposition to the plasma that kills the filament slowly. And I think this is what we need to work on to increase the lifetime of the filament.
Okay. Some question in the audience. I will give you the right, just so Yevgeny is asking a question. Where is Yevgeny? Ah. Yevgeny, you can talk.
Okay, can you hear me?
Yes.
Okay, Tatiana, thank you very much for your talk, interesting talk. So my first question, I have two question and comment. My first question is about your computational work, and but specifically, it looks like from your simulations, I'm not familiar with your code. It looks like from your simulations, your magnetic field lines or surfaces are almost equipotential, right?
Yes, but it actually really depends on the anode location.
But how do you, it's a true two-dimensional code, or you assume some conditions along the field lines?
It's well, we provide the magnetic field, and the results tend to be almost equipotential lines matching the magnetic field, but not necessarily. And you can see on the right figures that it's the equipotential lines are trying to stick to the magnetic field, but they are a bit affected by the anode. I'm not the developer of the code, so if you're interested, I can give you a reference with more information.
This would be wonderful, but my question is more, you know, like we heard it yesterday, and we published results about it before. In cylindrical thrusters, field lines depart from equipotentiality quite significantly. So basically, it's not clear if E equals V cross B is sufficient to explain operation of this thruster. And so I understand what you just beginning, but but what effects in your code? If you don't know, it's okay. I will try to reach Eduardo and check with him. But what effects in your code basically implemented? So do you include gradients of magnetic field in radial direction? So do you have mirror effects or anything which included?
Yeah, we included the full magnetic field. So yes, we can potentially have mirror effects, but it's not obvious to see it in the results.
Mm-hmm. And then, okay, thank you. And then a second is a comment. Did you try to, first of all, what kind of filament do you use? Tungsten or thoriated tungsten?
Thoriated tungsten.
Mm-hmm. So this may be kind of good, but did you try to vary distance between filament and the thruster?
Not yet, but we definitely need to, because first of all, because of this contamination problem. So we don't want to completely ruin our channel because of the filament, the tungsten depositing. But yeah, we definitely need to try. The issue is that the ignition is quite hard. We really need to heat up the filament a lot in order to break down to the anode to create the plasma. And after that, it goes very well. But the ignition, yeah, it requires a lot of heating.
Mm-hmm. You mean you have a hollow cathode, right, in your experiments, right? In principle. So you could do it easy to start thruster with hollow cathode and then to introduce filaments. So to stop hollow cathode flow and everything, to introduce filaments. This is tricks which we used, in order to simplify ignition and not to have coatings like that.
So when you tried yourself with the filament, you ignited first with the hollow cathode?
Yeah, and then you stop it and continue with the just filament.
I see.
Okay.
Okay, thank you. Thank you for the comment, Evgeny. Okay, so I think that we have to switch to maybe one last question. Yes. Yes, you can talk.
Okay, thank you for the nice presentation. I have a quick question about your 2D simulation.
Mm-hmm.
How did you give the anomalous collision frequency in your simulation?
So we have in the election fluid model, we have 3 equations. So we have the momentum, energy, and heat flux, and so we have in each of them we have a parameter. It's done the traditional way. I mean, the way that most people do it. We just include an anomalous frequency, an extra frequency that is function of the plasma frequency, and we set an arbitrary percentage to define this parameter, and it can be different for each equation. So yes, the only thing that is that we don't know actually what value we should use, and if the value should be the same in each equation or not.
Okay, thank you.
Okay,
no
so we can thank again Tatiana for his
Thank
talk.
you very
And
much.
yeah, you're welcome. And now we have to switch to the last speaker of this morning session. The last speaker is Arturo Popoli from the University of Bologna in Italy, and he will talk about numerical simulations of a 50-watt annular Hall thruster. Please, Arturo.
Okay, thank you very much. Do you hear me?
Yes.
Do you also see the screen shared?
Yes.
Okay, perfect. So, one second. Okay. So, thank you very much. Yeah, again, I'm from the University of Bologna, but actually this work started out when I was a visiting student at Laplace under the supervision of Dr. Garrigue. And also this work is a collaboration between Laplace and Prof. Cho's group at KAIST in South Korea. Okay, so I will start with a quick outline of the presentation. I will give you just some quick information about the thruster that we have considered for this simulation work. And then I will introduce HALIS, which is the code that we used to perform all the simulations, which is a hybrid code. And so I will give you a bit of background on the different techniques used to model ions and electrons. And then finally, I will discuss some simulation results, also in comparison to the measurements that have been made at KAIST by our colleagues. So, as you can see here, this is the same thruster that has been discussed yesterday by Donggo Lee. And yesterday, actually, he talked about two different magnetic topologies of the same thruster. So in order to be clear, today we are only discussing the second one that you showed yesterday, which is the one, so to speak, with the convex lens topology that you can see here. The thruster is a really small scale one. It works in the 50-watt class, and it has dielectric walls. And as Donggo discussed yesterday, it exhibits two different operational modes depending on the anode voltage and the flow rate. So in this work, we are only going to focus on mode B, which is the one that exhibits a shorter acceleration zone and higher thrust, anode efficiency, and specific input. So the goal of our work was to see if we were able to simulate and predict the performances of the thruster with a hybrid code. Now, coming to Hallis, Hallis has been developed through the years at Laplace. I leave here in the bottom of the slide one reference for the model. It uses
sorry, Arturo, we don't see your slide about Alice.
Oh, okay. I don't know. I can stop the screen sharing and share it again. Do you see now?
Yes, we see it.
Okay. So in Hallis, again, a kinetic approach is used for the neutrals and the ions that are represented on a grid. And in this case, we are talking about a grid with the axial and radial dimensions. So we are taking advantage of the azimuthal symmetry of these devices. And we represent the real particles with macro particles that we can follow the trajectory. And also, by integrating the trajectory in time, we can also follow their interactions with walls and also their collisions, which are modeled with a Monte Carlo collision approach. Now, the main advantage of this is that we can consider the macro particles as samples of the velocity distribution function. So we don't have to make any assumptions on the distribution function itself. The disadvantage, however, is that, as we know, particle models are particularly computational intensive. So a different approach is instead applied to model the electrons, and this is a fluid approach. So we have to make an assumption on the electron energy distribution function.
Yeah,
now,
sorry.
Can you see now the slide?
No.
Oh, this might get complicated. Okay. What do we do? Maybe if I take out the full screen now, can you see it?
Yes.
Okay.
I will see it now.
Okay, so I will do the presentation without the full screen.
Yeah.
I'm sorry. So then, here, under the assumption of Maxwellian electron energy distribution function and of quasi-neutrality, so we work with a quasi-neutral model, we can write out the fluid conservation equations for the number density, the momentum that here is expressed in the diffusion form, and for mean energy. And also, we make a further assumption, which is also known as Morozov approximation or thermalized potential. And this assumption is that since the electrons, unlike the ions, are actually magnetized by the magnetic field, we can assume that along the magnetic field lines, the electric force is balanced by the pressure gradient. And in this way, we can define a constant thermalized potential along the magnetic field lines, and we say also that the electron energy is constant along the magnetic field lines. We introduce a stream function lambda that is, again, constant along the magnetic field lines, and this allows us to define a quasi-1D grid. We define a grid which corresponds to the magnetic field lines, which starts with the anodic magnetic field line and ends with the cathodic one. And then this allows us to solve the fluid equations on this quasi-1D grid. The advantage of this is that, of course, we can save a lot of time by not applying a particle model to the electrons. But the disadvantage is that because of this, we must provide some suitable expressions for the electron transport. However, we know that this is kind of an open issue because the classical cross-field electromobility, which takes into account only collisions with electrons and neutrals, between electrons and neutrals and Coulomb collisions, doesn't really yield results that are in agreement with experimental measurements. So we have to find some way, a way to increase this mobility. And in HALIS, this is performed in 2 steps. So first of all, there's an anomalous collision frequency contribution, which is added inside the channel to take into account the electron walls in the electron wall collisions, and a second contribution, which we can call a bomb-like contribution outside the channel, which takes into account generally turbulence and instabilities. So we can see that now we can redefine the collision frequency in this way, and we have 2 constant parameters, alpha and kb, which we can set to enforce the importance of the anomalous transport, again, inside and outside the channel. So now here I had some animation, which we will lose, but the point is that we decided to perform a series of parametric simulations to understand a bit the effect of these parameters and to correlate them with the performances of the thruster. So we explored a range of the 2 parameters, alpha and kb, and you can see here the thruster performances as a function of these 2 parameters. And now this was interesting because we can clearly see, for example, let's consider the effect of the alpha to kb ratio. We can see that if we increase this ratio, we basically regulate how much of the voltage drop takes place outside the channel exit. And this, if you think about it, it kind of makes sense, because if we increase alpha, it means that we have more anomalous transport inside the channel, which means that we have a higher conductivity, and then the voltage drop is more likely to occur after the channel exit, where we have a higher resistivity. Likewise, I think it's interesting to see what happens if we increase both alpha and kb. So if we have a lot of anomalous transport, both inside and outside the channel exit, we can see from here, from the contours of the discharge current, that we have an increase of the discharge current, of course. But then, if we look here at the ratio between the ion current and the discharge current, we can see that really this increase is almost completely due to the electron component. Which means that the ion component basically stays the same, which in turn means that our thrust will remain constant, as you can see it here. However, our anode efficiency will inevitably decrease because we are increasing the thrust, because we are keeping constant the thrust, but we are increasing the electric power, okay? So, after this, after we collected all the results of the parametric simulation, we selected like 2 best cases, so to speak. And the one is, case 1 is defined as the case where we have the best match between the computed and the measured thrust. And case 2 is the one where we have an overall best matching between the thrust, the anode efficiency, and the discharge current. And here we can see the computed performances for case 1 and case 2 compared to our reference, which were the measurements provided by Prof. Cho's group. And we can see that in both cases, we have a really good and close agreement between the measurements and the experimental results. However, this was not the end of our study, because we also had available the measurements of the ion's speed. So we thought that it might be the case to check also if these were coherent with our results. So we can see here a comparison between the anomalous collision frequency on the right for the 2 different cases. And we can see first that the classic contributions are pretty much similar in the two cases. And also we can observe how important are the anomalous contribution in determining the overall collision frequency, which is in black. And here on the left, we can compare the velocities, the obtained velocities for the two cases with the LIF measurements. And we can see that the results are not at all compatible, which means that we have a problem because our approach allowed us to represent the global performances of the thruster, but we are wrong in determining the acceleration structure. So we had to slightly change our approach. And we decided, instead of using constant parameters inside and outside the channel exit, we decided to manually enforce the collision frequency profile that you can see here in pink. And this led us to have a compatible velocity profile of the ions. But however, we solved one problem, but we end up to having another. Because now the performances were not really comparable to our reference, so the measurements. So we repeated again the procedure by not only making sure that the velocities were correct, but also enforcing that the changing iteratively the anomalous collision frequency so that also the discharge current was compatible with the measurements. And then this was an interesting result for us because by only setting these two parameters, then we found out that also the thrust and the, of course, the specific impulse, but also the efficiency were compatible with the measurements. Okay, so another experimental information that was available from the measurements was the doubly charged ion current fraction, which was around 10% in the measurements by our colleagues. And we compared it with our results. And as you can see, again, this is comparable, which is a good result for us because it means that not only the acceleration structure is more or less correct, but also the kinetic the kinetic process to get to the doubly charged ions. And it means also probably the electron mean energy. Then also another interesting point is that, of course, we have two different kinetic channels to produce doubly charged ions. We can consider the direct ionization from ground state, but also the stepwise ionization. And now, as you can see, these two processes have quite different energy thresholds. So maybe we could expect that this second process, the stepwise ionization, would be more important. But as we can see, the two processes are comparable. And I believe that this is because since this is a small-scale thruster, we don't achieve the same levels of ionization that we could get in a full-scale thruster. And as you can see here, even in the region with high radial magnetic field, we get still relevant densities of xenon. So that allows for the also the ground, the ionization from ground state to be relevant. So coming to some conclusions, in this work we simulated a miniaturized Hall thruster, and we tested like two different approaches to model the anomalous collision frequency for the electron transport, and we were able to have a good compatibility between the results and the experimental measurements once we introduced two different constraints, one on the discharge current and one on the velocity of the ions. So what's the takeaway of this experience? I think the most interesting point is that since we used a non-self-consistent model, we have to take into account that we cannot rely when we use a non-self-consistent model only on, let's say, I will call it macroscopic information, so on the measurements of thrust, power, current, etc. So if you want to use these kind of models, we also need to have some kind of, let me call it, microscopic information about the physics that is really going on inside the thruster, okay? Because we need this to have a coherent results, okay? So this tells us about how important, for example, in this case, the LIF diagnostic is even to the simulation process. Okay, so I think I'm out my limit for the time, and so I will thank you very much for your attention, and sorry for the technical issues.
Thank you, Arturo, for your talk, interesting talk on annular miniaturized annular Hall thruster. So now we have time for a few questions. So in the audience, please. There is one question from one anonymous spectator. I'll tell you the question, Arturo.
Mm-hmm.
How long does it take for one simulation case to converge?
Well, I would say now we have to take into account that these simulations are not parallelized. So for one simulation with a reasonable amount of macroparticles, I could say I should say a couple of hours, which again, I think that this explains you why we stick to non-self-consistent models, because if you had to do this with for example, a particle in cell, a full kinetic model, of course, this would take you a lot longer. And this is why these kind of models allow also for parametric simulations, because they converge quite quickly.
Thank you, Arturo. Other questions, comments? So, Unwo?
Thank you, Arturo. Very nice presentation, because this is the 2D simulation. Probably in your next presentation, I'd like to see the 2D pictures of the potential profile to figure out the ion acceleration, ionization, and so on and so forth.
Okay. Okay. Thank you. I actually have them, but I didn't know if I had the time.
Yes,
the time to show them.
But, please, do it.
So here you can see them. We have, of course, so we can see that we have a relevant electron density, and also the electron energy that goes up to 30 electron volt. And also we have that, as you can see, we have here the bulk of the ionization. Now, in this term, I didn't split up the two contributions to the ionization. So we have xenon 2 plus and xenon plus together.
Okay, thank you. Another quick question is, how difficult do you think is to simulate the cylindrical Hall thruster case?
The cylindrical Hall thruster is a bit more difficult. We actually started out to do some tests because we had. Let me go back here. In the cylindrical Hall thruster, we have a different magnetic topology, which for us it is a slight complication, because if you can see here we have both grids, the particle and the fluid grid, and we know because of our approach, the fluid grid is limited by the magnetic field lines that intersect the anode and the cathode. So in one way, we have to be lucky to find a magnetic topology where the two lines allow us to have a domain which is of a minimum size that allows us to see the physics. So we started out, we are carrying out some tests, but so I will say it is not impossible, but we need some work to do it.
Okay, thank you very much.
Thank you.
Nice work.
There is one question also in the audience. So, what is the advantage of your code compared to already existing, and why to do one more code?
Okay. First of all, this code is not mine. I want to state clearly that it has been developed at Laplace. So I'm a code user. So I don't want to take credit for the code. I think that nowadays there are also. I mean, this is now a kind of code. There are many hybrid codes. This is not the only one. Of course, the main point again is that there is a trade-off. These codes can still be useful because they can allow us to do parametric simulations because they are really fast. We pay this by making assumptions on the anomalous transport. So why should we do more codes? Because the ideal alternative to this kind of codes or approach, it would be to use full kinetic approaches. But so far, or even if we consider, for example, 3D, it is not feasible yet unless we are able to speed up the calculations a lot. So I think they are an interesting way to work until we know how to run our our kinetic codes much faster.
Yeah, and if I can add a comment also about the last part of the question, I have to say that this code was one of the first that has been developed in the community after the code of 5 and the code developed by Eduardo at Madrid. So I think it is not one more code, but it was one of the first hybrid code developed in the context of modeling of all-thruster simulation.
And also maybe I add just 2 words. I think the first applications of this code were for a standard scale thruster. And so part of this approach and also the idea of performing parametric simulations was taken from that case. Now we applied it to a thruster that we know it is completely different. Small scale thrusters have a different magnetic field. They have also some kind of differences in the physics. And it is interesting that we were able still to apply the same concept to a thruster which has important differences.
Okay. Thank you. So I think that we can close the session. So we thank again all the speakers.
Thank you very much.
And now we start again at 2 p.m. So it's the end of the session. Thank you again also to the audience. So have a good lunch and see you later at 2 p.m. Okay, bye.